Hello, everybody. How you doing? Welcome. And if you guys are ready, I'll go ahead and get started. And we are doing, hi. Hello. So I bent to your guys as well. We're going to have the review. And actually, this was the suggestion of another student to have a Zoom instead of a YouTube, because you can watch the YouTube recording anyways. So this is really an opportunity for you to ask questions if you have any questions from the study guide. And then at the very end, I'm going to go ahead and go over those 10 advanced questions. Okay. So, all right. Do you guys want to, you have a preference for how you want to start? You want to start with chapter 10? Should we start at the beginning?
Yeah, start and definitely go in order.
Okay, go in order. Okay, sounds good. And if you guys are not asking a question, if you want to ask a question, you can ask it in the chat, or you can turn on your mic. But if you're not talking, then turn off your mic so that we can not be confused. So I'm going to go ahead and highlight my view. I think, how do I do that again? I got to go like this, spotlight video. So the other people can see this on the YouTube channel. Do you guys see me as spotlighted or no? It's just me. Never mind. I know. You guys can see whatever you want. You can go to speaker view or whatever. Okay. So anyways, I'm not an expert. Okay, but getting better. So we have a test coming up Tuesday. Let me just explain the format of the test, because a lot of people are asking. I did post some information. Actually, I could just jump over to the Canvas if you guys want to take a look. Take a look on the Canvas. We'll look on, they're the same for both classes, so it doesn't matter. But exam 3, if you go down here, so here is exam 3. Here it is, right here. You can't get in, and I've already taken the test myself. I did pretty good, although I missed a question. I can't believe it. I made a mistake. I misread it. Anyway, so just be careful. But anyways, this is the information here. You get 80 minutes from the moment that you open it, and you can open it at any time on Tuesday. So it'll be open at 12:01 a.m. and close at 11:59. So, you know, if you want to go crazy and take it at 12:01, be my guest. You could wait until you wake up in the morning and then take it. But it's anytime. It is open notes because I can't monitor your notes use, so I'm going to make it open notes. You are allowed to, but please don't communicate with other people. Okay, you're not allowed to ask other people what the answers are. That's cheating. Okay. And if I have not changed your time, you should see the appropriate amount of time. If you're a DSPS student, please let me know, and I can change that during the exam, actually. So while you're taking it, you won't be disturbed if you just sent me a quick email. I'm going to go look at them and check them by Tuesday. So I should have given you the extension. If I forget to do it, though, please let me know. Okay, so meanwhile, here's the study guide. Let's take a look at the study guide. Actually, oh, I downloaded. Okay, that's fine. Take a look at the study guide. Where is the study guide? What study guide? Oh, it's the 4th time I've downloaded it. Okay, so can you guys all see the study guide? Anybody? Just shake yes. Okay. No, you cannot. Okay, let's try it again. Let's do this. Let's share the study guide. Oops. Okay. This is what I do wrong, right? I click the link and then assume you guys can see it, but you can't. Okay, so starting off with actually just before chapter 10. Thank you, Ashlyn, for your suggestion. This is because of Ashlyn, everybody. But anyways, you're supposed to know a few things about the New Horizons mission, right? That was the mission that went to Pluto and beyond, right? It went beyond. Oh, I forgot to change the name, darn it. There's a new name now. What's the name again? Oh, darn it, I forgot to change it. Okay, I forgot. I forgot to put it on your test anyway, so don't worry about it. But anyways, okay, so the New Horizons mission went to Pluto, and Pluto now is considered to be a Kuiper Belt object. What's a Kuiper Belt object? An object found beyond the orbit of Neptune. And Pluto and its largest moon, Charon, is pretty important. But we also went to Ultima Thule, which is not Ultima Thule anymore. What is it renamed? I forgot the name, darn it. Ultima Thule. Arakoth. Okay, here we go. Arakoth. Can you guys see this? No, you can't. Okay, the name is. This is the new name, Arakoth. Okay, but I didn't put it on your test, so I'm sorry, I forgot it. Okay, don't worry about that then. Okay, so back to our study guide. So Ultima Thule, also called Arakoth. Okay, describe some of the major discoveries made by the New Horizons flyby. So if you remember, I kind of gave you a few highlights if you'd like. Somebody want to give me a thumbs up or something? Do you want to just quickly go through that slide set again? It's just a very small slide set. We could just look at that if you guys want to highlight the few things. It's just a few things. So let's just do it. I think it's probably faster than me trying to remember everything. But it is the New Horizons. Oh, there I had it. Okay, shoot. Okay. If I had only taken a look. All right, so let me just bring this up and you will see the New Horizons. Okay, so here is the slide. Okay, and you can find these on Canvas too. These are found on Canvas. So Clyde Tombaugh discovered Pluto in 1930. And it's very far away. This was the best picture, and then we sent this mission called New Horizons, and the New Horizons went there, and obviously went very fast, so fast that it couldn't stop, and so it just flew past, and it was July 2015 when it flew past. Okay, and we got the best picture of Pluto that had ever been seen. I don't know why I can't. There we go. So this is a good picture. This heart-shaped object is the largest glacier in the solar system, and it's made of nitrogen ice. That's one of the things you should know about, right? And it's called, what is it called? It is called, I forgot. Who knows the name? Anybody? I forgot the name. It's called, oh, darn it, I know the name. Nitrogen ice glacier is called, I forgot. Okay, biggest nitrogen ice glacier ever. I forgot the name, darn it. Okay. It is has an atmosphere made of mostly nitrogen, but it has a little bit of methane and carbon monoxide, and it actually has a bluish color, if you could see that. The methane, of course, is a greenhouse gas, and when it's in the atmosphere, will give a little boost to the greenhouse effect on Pluto. Pluto is highly affected by its orbital position. Okay, so its atmosphere is very, very weak. Oh, somebody's going to give me a question. Okay, here, tell me. Yes, Sputnik Plenum. Thank you, Anna. Sputnik Plenum. Thank you. I don't know why I forgot that. I guess the name is not really that critical for you though. So, but the atmosphere is enhanced being close to the sun, and as it moves away from the sun, like a comet and its coma, it will fall out of the atmosphere and solidify, deposit onto the surface. So the reddish color on the surface of Pluto and Charon is actually these hydrocarbons that were originally in the atmosphere. Okay, so here are some of the cool pictures, just interesting. There's mountains and plains and interesting stuff. So here are some of the things. There are ices of carbon monoxide, nitrogen, water, and methane. And these, there are, for example, these blades of methane that are hundreds of feet tall. And then this is one of the big things. The mountains are made of water ice. Okay, so not of rock, not of silicates. They are, 11,000 feet. They're not as tall as the mountains on Earth, but it doesn't matter. They're just mountains made of water ice. Beautiful, interesting. Has 5 moons, but the moons have very interesting orbits. Other than Charon, and Charon is very large compared to Pluto, so large that it's been tidally locked to Pluto, but Pluto is tidally locked to it. That's a very interesting thing. So the two objects dance around each other and are always facing one face together. But the other 3 are really, really small. So there's Nix, and there's Hydra, and there is, what's the last one? Nix, Styx, and Hydra. There we go. Nix, Hydra, Kerberos, and Styx. And those orbits are very strange because they're unpredictable. They're chaotic orbits. Okay, so that's what you're supposed to know. So Charon, beautiful, big body. There are some crater-looking things, but mostly it has lots of smooth areas. So it's pretty young. It does have a giant rift valley around the middle, and this reddish color is an organic compound that comes out of the atmosphere of Pluto, and probably also it has some. It may even have a little atmosphere as well, but we've never seen that. It meaning when it's near the sun, so don't worry about that. But anyways, here's a picture of them together, and you can see they're roughly, you know, they're similar size, about half the size of Pluto. But Pluto is small, right? It's the size of a moon, really, the size of our moon. Okay, so what are the mountains on Pluto made of? Water, ice. Okay. New Horizons launched at high velocity. Okay, so why did it not go into orbit? We said because it's launched at high velocity, but it didn't finish its trip at Pluto. It shot past and continued on, and the object that it went to was originally called Ultima Thule, and now it's called Arrokoth. Okay, so those are kind of the big deal ideas, and you don't really even need to know this either. I forgot to ask a question on Arrokoth. That would have been a good question. Maybe I'll find a question I don't like as much, and I'll put in a question on Arrokoth. If I have a last minute change, I could still edit it before Tuesday. We did have one really powerful result, though. It turns out amateur astronomers helped observe this as it was passing in front of stars, and they were able to see that it had two different lobes that are connected together by this little neck material. So anyways, it's kind of interesting. It looks a lot like that Rosetta comet that we saw as well. Okay, so that is pretty much it. That's it. Okay, here's the best image ever taken of a Kuiper Belt object. Okay, so those are kind of the highlight ideas that are found in that slide set. Okay, so let's keep going. Everybody good? All right, back to our study guide. So describe some of the major discoveries. How has this changed our understanding? Well, they're much more interesting than we thought, right? Is Pluto alive? What would you say? Would you say it's alive? Anybody? Since you guys are live, you can tell me. Is Pluto and Charon, would they be alive? And I would say the answer is yes, because the surface is changing, right? That's enough. If you see something where the surface is young and changing, then that's basically a sign of life. Okay, so the name, blah, blah, blah. Okay, this is not Ultima Thule anymore, it's called Arrokoth. Okay. All right, so jumping to chapter 10 now. We are on the sun. The sun is a star. What is the sun made of? Well, the sun is a mass of incandescent gas, a gigantic nuclear furnace, right? And we turned out that that was wrong, right? What's a better way to talk about the sun? Not gas, but first word, plasma, right? And so the song by They Might Be Giants does show up on your exam. And so you need to know two versions of the song. What was the sun is a massive incandescent gas, but that was wrong. And so the correct version was the sun is a miasma of incandescent plasma. What does the word incandescent mean? Anybody help me out? Maybe you remember. Got a few people watching on YouTube. You could go ahead and put in comments as well. Okay. So if you, the sun is a mass of incandescent gas. Nope. It is a miasma of incandescent plasma. All right. So, and back to this. Okay, thermonuclear fusion, what is that? That is the process of hot gases, hot plasma, taking individual nuclei and merging them together to form new nuclei. And in the process, releasing energy. This is the process that's going on right now in the core of our sun. Okay, so then we got the next term, hydrostatic equilibrium. What does that mean? And as long as a star is alive, the force of gravity is pulling in, but there is a force pushing out, and it is just as large as gravity, exactly balances gravity. And what is the name of that force? It is called, the word right here, radiation pressure. So when the star is alive, the radiation pressure pushing out balances the force of gravity pulling in. They're exactly balanced. It's called hydrostatic equilibrium. All righty. Let me see, we could do something more fun than just me talking, right? Let's see if I can find a little animation of the sun. Let's see if I can find that animation. Let's see, can I find an animation? Trying to find a different, oh, that's the one, but oh well. Trying to find an animation, but I'm not really finding one. Let's see if I can find one. Differential rotation. Oh, I've got NASA. NASA's cool. Let's see. This is differential rotation. Oh, that didn't work. Fail. Okay. I should have just looked for it. All right. Well, so we'll just look at an image. Go to the images. This is probably the best one. Okay. So we're looking at this picture here, and you guys can't see it yet, but I will go ahead and talk about it right here. Hold on. New share, differential rotation. So here is the differential rotation. These are the lines of the magnetic field of the sun. We're going to talk about this in just a minute too. Actually, whoa, there's a video. Should we try that? Anyways, so what happens? The rotation of the sun is not the same for every part of the sun. It depends on the latitude, right? So the equator is 0 degrees. If you go north or south, then the rotation period increases. It goes slower, right? So it rotates fastest at the equator and slowest at the pole. And it's about 25 days at the equator and 35 days. They put 36. I don't know, 35, 36. I'm not really that worried if it's not exactly 35 at the pole, okay? And so what happens? You see that the lines start to get tangled up as a result of this. It's called differential rotation. It's kind of, we gave the analogy of like twisting a rubber band. And as you twist the rubber band, you twist, 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 it suddenly bunches up. And that, we think, is what causes a sunspot to form. So should we try this? I don't know if this is going to be any good, but I feel like, you know, let's just go for it. Let's just try it. Why not? So this is, there's no sound. There's no sound anyways. Oh, it's kind of an animation. Yay, that's kind of what I was looking for. And then if it bunches up, yeah, as soon as it bunches, ooh, that's kind of cool. Maybe we should see this too. Just never mind. I don't want to watch an ad. Okay. I don't really want to watch an ad. Okay. So back to my study guide. Okay, so differential rotation is the term for what we just saw, that the different latitudes of the sun rotate at different rates. Okay. Here are the parts of the sun, the core. Can't select. Oh my gosh, that's funny. There we go. These are the parts of the sun that you need to know. There's a core, radiative zone, convective zone, photosphere, chromosphere, corona. And again, probably the best thing would be to just show you a quick picture. So if I go to the PowerPoint on the sun, you guys could follow along with me. This is our picture. Let's go ahead and switch. My screen share is paused. I don't know why. Here we go. Were you guys able to see it? No? Okay, let's try it. Let's try this. Here we go. So here are the parts of the sun. You guys remember? We got the core in the middle. That's where fusion is taking place in main sequence stars. Outside of that, we have the radiative zone where the light, the photons are trying to escape. They really have a hard time getting anywhere. because the matter is so dense here. And so they get trapped and then recreated as a slightly lower energy. So the original photons that are being created in the core are very high energy gamma ray photons. And when they finally escape from the sun, they're visible light. So they're much lower energy. So the radiative zone, they're primarily trying to escape by radiation. When you get finally to this area right here, the top of the radiative zone is the bottom of the convective zone. And now the sun has traded radiation for convection. And so now we have circulation taking place. And that circulation is known as convection. So hot plasma at the bottom of the zone will rise and then release its energy and then fall back down. And a single convective cell is called a granulation, right? Let's see if we can see that. Let's look for too many things. This is all inside that chapter. Okay, wow. Never mind. I should just let me go find the PowerPoint slide if you guys want to see that. So granulation is, here we go. All right, hold on, coming right back. Let me share that slide with you. Okay, so this is a single convective cell, and it is hot in the middle. It's brighter and darker on the edges. And what's going on is the hot plasma is rising and the cool plasma is falling. Okay, so hot and cool show you are seen on the sun as brighter and darker. Okay, so there's a dark boundary and a bright middle for these convective cells. I have to stop. Oh, there we go. Gotta go back. All right, so we got to radiative zone, convective zone. I forgot to tell you about the photosphere. So just 1 second. Let me go back to my PowerPoint again. I guess I should have talked about that. And I will get back to that picture then of the sun. All right, here we go. Switching back to the sun. Here is our sun. If you can see the sun, we got the convective zone. The top of the convective zone is what we see. It's the light of the sun is coming from the top of the convective zone, but we call that the photosphere, right? So the light is coming from the photosphere. What colors come from the photosphere? All the colors of the rainbow, right? White light is coming from the sun. If you can see, the sun has an atmosphere around it, and that's a very high, that's a very hot gas, and it's actually kind of pink in color, called the chromosphere. And it's kind of close to the sun. Much further away from the sun is this very low density area called the corona. Okay, so core, radiative zone, convective zone, photosphere, chromosphere, corona. The corona, by the way, has a temperature of almost 1,000,000 Kelvin, which we can see using X-ray telescopes or X-ray cameras. But we can't see the corona except when we have a full solar eclipse. Okay, that's one of the things you're supposed to know. All right. Just if you have questions, raise your hand or put a comment so that I can see that. And I will go ahead and try to address your questions when you do that, right? Okay, let's see. I think I messed up my YouTube link though. I can't see the YouTube. Oops. Okay, give me 1 second, sorry. I just want to make sure I can help the YouTube people if they have questions. Okay, exam 3 review. Here we go. And here's my YouTube link. Okay. Thank you. All right. So YouTube people, if you have questions, make sure you're asking them. Hello. Hello. Nobody's saying anything. Okay. So anyways, all right. So back to our study guide. Okay. So photosphere, chromosphere. Okay. Strong nuclear force. This is a topic that we kind of segued off of. And let's go ahead and take a moment and segue again into the strong nuclear force, okay? So I'm gonna go ahead and switch cameras to this one facing down so I can write stuff, okay? And I It just fell down a minute ago and now it's okay. All right. So what are the forces that you guys are supposed to know about, right? Obviously, that one that we mentioned, the strong nuclear force. Let's talk about that. Okay, so what are the forces that you know about? Gravity. It is actually the weakest, but the longest range. Longest range. That's why it's so great at organizing the universe and making stars and then eventually making galaxies. The electromagnetic force, right? I don't need to write the word force every time. These are the four fundamental forces in the universe. Okay, the electromagnetic force, and this is much stronger. And what is it good for, right? But a shorter range. Shorter range, much shorter range. Okay, so this is the one that we're kind of gonna talk about it a little bit, right? Because it's the one that attracts the negative electrons, for example, are attracted to the positive nuclei. That's one of the ideas. Or if you want to talk about the fusion process, if you take a hydrogen ion, positive hydrogen ion, and another positive hydrogen ion, do they want to go together? And the answer is no way, because they repel each other. The electromagnetic force is repulsive. But you can force them to go together if you give them a fast enough speed. Where does the speed come from? It comes from the temperature, right? The temperature is hotter, then they go faster and they smash together. Something amazing can happen, right? So this is number one, number two, number three, right? What happens if you force two protons right next to each other, right? Another force steps in and holds them all together. And this is called the strong nuclear force. So one of the things, I just wrote the word force again. Okay, whatever. Strong nuclear force. Okay. One of the things you're supposed to know, it is stronger than the repulsive force, right? It holds the nucleus together, right? That's one of the things that it does. It actually does something else too. And actually, this is the segue that we went on. But let me go ahead and add one more thing. The fourth force is called the weak nuclear force. And again, I wrote the word force. Okay, but what does it do? It controls, it's something, blah, blah, blah. It explains why a single neutron, free neutron, will decay. Okay, so you might not remember, but if you don't remember, now is the time to remind you that if I take a neutron, which is neutral, something amazing happens when you take it outside of a nucleus. Inside of a nucleus, it is completely stable, but outside of a nucleus, it decays and turns into a proton plus an electron plus an anti-electron neutrino, right? This is the anti-electron neutrino. I don't think you need to know that so much, but what you really need to know is you get a proton and an electron coming out. That's crazy cool, okay? So what else do you need to know? So that's just about it for the weak nuclear force. And then later on, the reason why we learned this is because we learned that if a proton and an electron are forced together along with an electron antineutrino, don't worry about that, what can happen is you can get a neutron. That's how a neutron star is going to form. Okay, so because of this, this is also true. Okay, so let me just briefly take you down on that journey that we learned a little bit about the strong nuclear force, because it actually does something else. And you don't have to know a lot, but just a tiny little bit. It also holds quarks together. And there are these things called quarks. And it turns out that a neutron or a proton is made up of 3 quarks. And there are actually only two types of quarks, up and down quarks. And you don't actually need to know all the types of quarks, just this idea. This is kind of an amazing thing, and I just wanted you to be aware of it. So the way it works is an up quark has a charge of positive 2/3 of an elementary charge, and a down quark, so we use a U, right? A down quark is a charge of negative 1/3 of an elementary charge. So what 3 quarks do you need to make a neutron? And the answer is a neutron, which is 0 charge, has to be an up and a down and a down, right? You take a positive 2/3 and a negative 1/3 and a negative 1/3, and you get 0, right? So that's how you make a neutron. That's the combination that makes a neutron. Okay, how do you make a proton? A proton is exactly up, up, down, right? Positive 2/3, positive 2/3, and negative 1/3. Okay, and that equals positive 1 elementary charges. Okay, now why did I tell you that? Well, because it turns out that you need to know about antimatter. Okay, and I want you to understand exactly how this works. So we learned that there's this thing, so there's an electron, actually the antimatter version of an electron. This is an electron, this is the electron, but there's an anti-electron. And what is true about it? Well, antimatter has the opposite charge as the matter. And so it is actually a positively charged particle. And what is it? It is called a positron. You need to know that. You need to know that word, positron. Positron is an antimatter electron. Antimatter electron. Okay, antimatter electron. So what happens when an electron meets a positron? What happens? And something amazing, right? Annihilation. They're just gone. Annihilation. They are gone. They turn into pure energy. Okay, and this is a pretty amazing thing that's happening. Okay, it turns out the same thing happens with a proton and an antiproton. This is the way you do an antiproton, which would have a negative charge, by the way. They also will annihilate. But what's happening is it's happening at the quark level. So the up and down, down, and then an up bar, down bar, down bar. These are the anti-quarks, right? So antimatter particles are made, at least in these ones, are made of anti-quarks, and they combine to annihilate each other. Okay, so I've gone off on a little tangent, and I've done as much as I need to do. So let me go back to our study guide, okay? Hopefully you remember some of that stuff. It's not a big part of your test. Do not even worry. Okay, so the proton-proton chain is the first cycle that we learned, and it's happening inside of all stars, and then the one underneath it, by the way, is also happening underneath all stars. Alt, how do I do that? Alt T. Oh, that didn't work. Okay, so these are both happening inside of all stars. Okay, inside of all stars, and so you want to be aware of that. So let's go ahead and see that process. Let's see that process. Okay, so I'm going to actually, instead of my slide, I'm going to go to Wikipedia, and I'm going to go nuclear fusion in the sun. Okay, and I'm going to put in the sun and Wikipedia. Okay, nuclear fusion. Just 1 second, please. And I'm going to show you. Okay, hold on. Okay, so I'm on the sun. It's really hot here. Just kidding. Okay, I am on Wikipedia, and I'm on this is the page called nuclear fusion. And you don't have to read all this, but it's something here that if you'd like to take a look, you can do that. You know, again, you don't have to do that. But if you slide down here, you see a lot of the things that we covered in class. This is actually a pretty important one. This picture right here is the nuclear binding energy, and a couple of things to understand about it, right? As you go higher, you get something that has more binding energy per nucleon, Remember that a nucleon is either a proton or a neutron inside of the nucleus. And this right here, the peak, is right around at iron 56. Fe is the symbol for iron 56. Everybody wants to be like iron, to be more efficient, to have higher binding energy per nucleus. And so these atoms over here can become more efficient by fusing together, and they go higher and they become more efficient that way. But if you look over here, U-235, U-238, if they try to fuse and make something heavier, that actually becomes less efficient. So in order for them to become more efficient, they actually break apart into pieces, and that's called nuclear fusion. So everybody, every element on the periodic table, when they undergo either fission or fusion, the one that they want to do is where are they on this chart, right? If they're lower, if they're on smaller elements, they want to fuse, and if they're bigger elements, they want to split, which is called fission. Fission, F-I-S-S-I-O-N. Okay, so here are the two mechanisms that you need to know about. Number one, this is called the proton-proton chain. And again, what's important? Is the whole thing important? No, the whole thing is not important. Although let's take a look, right? We got the red spheres, which are the protons. Is this too big? Oh, I like that. Well, I don't know if I like, yeah, why not? Well, I don't know. You know what, I think seeing the whole thing is better. Okay, the protons are the red spheres. The white spheres are positrons, which we just described is an antimatter electron. And then coming out of it is also a neutrino. And over here is a gamma ray, right, at different parts. You don't have to know every stage at all. What do you need to know? You put in 1, 2, 3, 4 hydrogen, and then there's 2 more, 5, 6, but those 2 come back out again. So let's not count them. Put in 4 hydrogen and you get out 1 helium. The net is 4 hydrogen go in and 1 helium comes out. And the most important part of this is that it releases energy. Why? Why does it release energy? And the answer is because the mass of the hydrogen is bigger than the mass of the helium. So that missing mass, the mass that seems to be missing, is actually converted into another form of energy. According to the formula, you know, E equals mc squared. Okay, so the next process is right here, CNO. CNO is a what we call a catalytic process, because you start with the carbon, and when you come back to the end, you come back to carbon again. So the carbon comes back. It doesn't get used in the process. So if you look right here, 1, 2, 3, 4 hydrogen come in, and 1 helium comes out. Same thing, right? Except it's a more efficient process. If you have a higher temperature, which means you need a greater mass star, greater than 1.4 solar masses, then you can actually use this process more efficiently. But what you need to know is every star actually uses both of these processes. Every star uses this one and this one. But smaller mass stars use this one more, and larger mass stars use this one more. Okay. All right, back to our study guide. Okay, so we covered proton-proton, CNO. Antimatter we've already covered, right? Antimatter destroys matter. A positron is an antimatter electron. A neutrino is a tiny little piece of matter that will annihilate an electron. I'm sorry, that's not true. It is created during the process of nuclear fusion. And what do you need to know about that? You need to know something pretty cool, which is that the neutrinos pass right through the sun. And so they're created in the core, but they escape directly. And so this picture, I shouldn't tell you, but I'm going to go ahead and tell you. This picture shows up on the test, right? This picture is on the test. And I'm going to ask you, to understand what's going on, right? So we make photons. These red colored arrows are the photons, and they're not getting out. But the black arrows go straight out of the sun. They're not stopped by the sun at all. They go shooting right through it. They're called neutrinos. They get out of the sun without stopping at all. In fact, we have streams of neutrinos that are coming through the Earth right now and actually passing through us right now. So day or night, we have about the same number of neutrinos passing through it. They're really incredibly difficult to feel, to touch, to hold on to detect. But we do detect them from time to time, and they are very large neutrino detectors that are deep underground, miles underground, actually, pure water detectors. You don't have to know much about that. Okay, and there's a question. Great. How do we detect them how do we detect them? We detect them with a, well, actually the detectors are primarily pure water. And so what happens is once in a while, it's very rare, and actually the frequency is about once per month, these detectors will absorb a little neutrino, and the neutrino carries energy. So there'll be a flash of light that appears when the neutrino gets captured. And so what they have is these giant chambers under the earth, deep underground, full of pure water. And there's nothing else that can go that deep, right? Only the neutrinos really get that deep. And so they look for little flashes of light that occur. So what's really kind of fun, and I didn't get a chance to tell you guys more about this, a little bit advanced topic, but in my life, neutrino detectors have just been, they didn't exist before I was alive. In fact, 1987 is one of the biggest events that I know about. In 1987, we had a really special event. A supernova went off, and in a few minutes, we had 9 detections in just a few minutes. Something, I think, is it 9? I might be wrong about the number. In one day, it was like 24 detections, and usually it should be 1 per month. And so everybody was super excited, and they were able to actually say, hey, astronomers, go look over there. Something's going on. We don't know what. But it turned out it was a supernova. And so in supernovas, there are many, many more neutrinos released than just a regular star operating. Okay. All right. So back to our study guide. Antimatter positive. Solar granulation, we talked about that already. That is a single cell showing convection in the sun. Okay, Maunder minimum is another idea from that chapter 10. It's kind of exciting. And it was that there are sunspots, that sunspot activity comes in cycles. Okay, so I'm going to actually flip back to that slide for you. And you can see this is the Maunder minimum. So if you look right here, the sunspots have lots of sunspots, not so many. Lots of sunspots, not so many. Every 11 years, you need to know that, right? This is called solar maximum, when you have maximum sunspot activity. And then we have not very much, and then maximum sunspot activity. At solar maximum, something funny is also happening. The sun's polarity is changing. And so every 11 years, the sun's polarity changes. So it takes 22 years to go through a single magnetic cycle of the sun, right? So that's actually kind of an interesting thing. And then, yeah, okay, so we'll go back to the study guide. Prominence, flare, coronal mass ejection. These are ideas. So sunspot, prominence, solar flare, coronal mass ejection. These are ideas you're supposed to know about. A sunspot is a place where the magnetic field of the sun is poking out. And actually, let me go ahead and switch to our downward thing and tell you guys the little story again. How does a sunspot form? Okay, so what happens is that the sunspot forms when a little piece of magnetic field pokes out of the sun, right? A little, actually, I'll make this. So actually sunspots come in pairs, right? That's the first thing. One of them will be a north and the other will be a south, like that. And then if you look at just one of them, kind of zoom in, right, we're going to see something interesting. The spot begins because there's a magnetic field that wasn't there before, okay? And so there's temperature inside and there's temperature outside. And before the spot was actually a real spot, these temperatures would have been the same, okay? And then the magnetic field comes, right? The magnetic field comes and does something. It changes the equilibrium. So the temperature produces a thermal pressure, right? This is the thermal pressure. It's coming from the temperature. And the temperature outside has thermal pressure, right? So in the very beginning, these would have been equal. And that's because the temperatures would have been the same. As soon as you add the magnetic field, something exciting happens, right? This pressure that was inside now gets this new pressure from the magnetic field, this magnetic pressure. And so if you look at these, they no longer are balanced. This one's going to be bigger. So what happens to a bubble where the pressure inside is bigger than the pressure outside? The bubble expands, right? So in the next picture, the bubble is going to expand, right? So it expands. And what happens to the temperature inside? The temperature inside goes down. As it expands, the temperature inside goes down and the pressure inside goes down. And eventually something incredible, right? You get equilibrium. Because this is lower, when you add the magnetic pressure, it balances the outside pressure. Okay, so then the magnetic field goes away, right? The magnetic field goes away, and now these are no longer balanced. Now, this is less than this, right? This is less than this. So what happens? This thing will shrink back down, and it shrinks back down to a small spot again, right? Until, and by the way, as it shrinks, it heats up until the pressure inside, again, is equal to the outside pressure. So a spot forms when the magnetic field shows up. The magnetic field causes it to expand and cool inside. And then when the magnetic field goes away, it shrinks back down and is gone. Okay, so formation of a spot is one of the areas that you're supposed to be able to explain the story. Let's go back to our share. Okay, solar max. Oh, sorry, I didn't go through this. Okay, prominence. Actually, probably just easier to show you the picture. One more time, let's just go. Actually, you know what? I don't like the one in the slide. So even though I haven't changed it, I don't know why. I should just do that. Solar prominence. Okay, I'm going to just show you a picture. And we're going to look at the picture here. Okay, so solar prominence is a loop of material that leaves the sun and then comes back to the sun. That's called a prominence, okay? A flare, this is actually a picture of a flare. It shoots out of the sun and doesn't really come back, okay? A solar flare doesn't come back. Okay, so now the big bad creatures, these things are amazing. These are so powerful. They're called coronal mass ejections, okay? Ooh, let's look at that. Yeah, that's a GIF, okay. Ooh, let's see that. See it? Is it working? Look for it. Anybody see it? Oh, I guess that was too fast. Oh, there it goes. Okay, that was weak. Sorry. That wasn't very good. Let's see. I've seen better ones. I'll bet these are good. Let's see this one. NASA. Oh, yeah, that's good. See this huge ejection here? This is the size of the sun, and they blow out immense amounts of energy, okay? So let's see, okay, so coronal mass ejections are the ones that are dangerous, okay? Solar max, maximum amount of sunspots, and it happens every 11 years. Coronal hole is something where we see the coronal mass ejection is often preceded by a coronal hole. If we look in the ultraviolet part of the spectrum, we can see the corona, the X-ray and the ultraviolet are where we see it, and we can see a coronal hole forming. Heliosphere is the region around a star where the magnetic field is important, and the heliopause is that region just beyond it. Okay, all right, so describe each layer of the sun and how heat energy is transported. So you want to understand we have conduction, convection, radiation, and which ones are happening inside of the sun. It turns out that we have radiation happening in the radiation zone. We have convection happening in the convection zone. And then at the top of the convection zone, we have the photosphere. And light is radiating from the top of the from that photosphere. So there is no conduction happening in the sun because you need solid material for conduction to occur. All right, just differentiate PP and CNO. I think I kind of did that for you guys. Smaller stars use this. Larger stars, actually, they use both, right? But this is dominant. And larger stars use this dominant. Every star does both. Okay, I think I've done this already. If you fuse iron or higher, what happens? You form an element that is less efficient, which means it absorbs energy, not releasing energy. Only elements that are under iron will release energy. Okay, so at each stage of its life, a star is going to establish hydrostatic equilibrium, which means radiation pressure equals the force of gravity. What happens when matter meets an antimatter? Annihilation. Okay, convection flow, I did that. I did this already for you. Why is the sunspot cooler? And the answer is super easy, because it has expanded and cooled. Okay, how do sunspots form from the tangling? I think I've done that too. Describe how the magnetic field reverses and sunspot activity. It happens at the peak of sunspot activity. Okay. If you guys have questions and you want me to stop on anything, let me know. Okay. Otherwise, I'm gonna quickly go past these. What are the stages? Right. The sun starts as a protostar, and then it finally starts fusion inside of the core, fusion of hydrogen in the core. That means it's a main sequence star. For about 10 billion years, it will last as a main sequence star. You had to memorize that. And then it will have 1 billion years as a red giant. That means it's a huge star, and hydrogen is no longer burning in the core. So here's a question for you. Why is it that hydrogen is not burning in the core? What good reason could we have for not burning hydrogen in the core? Anybody know? Super easy answer.
It used it up.
We used it up. Okay. Where did it go? Is it just gone?
No.
What did it turn into?
Helium.
It turned into helium. Okay. So what happens inside of a main sequence star is the core is slowly changing from hydrogen into helium. At the end of the main sequence life, you ran out of hydrogen. You can't fuse hydrogen if you don't have any. So you have a core of helium. So what happens to the helium core? Does it start burning? You guys will talk more about that in the next chapter, but the answer is not right away, right? In fact, as soon as you run out of hydrogen, what will happen? Well, you won't be making the pressure anymore, or not as much pressure anymore. You still have a lot of heat, but you won't be making any new energy. And so the pressure in the core will not be enough to keep it from collapsing. So the core will begin to contract, not exactly collapse, right? But contract. And as it contracts, what happens? It heats up. So eventually it will heat up and the helium will start to fuse, but not at first, right? It'll take a while. It's a big jump. In fact, the helium fusion temperature, you don't have to memorize this, but if you want to write it down, it's 100 million Kelvin. Hydrogen was only 10 million Kelvin. So what happens is the core begins to collapse or contract. Let me use the word contract instead. Contract and heat up. And then outside the core, you still have hydrogen. That hydrogen will reach a temperature of 10 million Kelvin and begin to fuse. You get what is called hydrogen shell burning. But that's no longer a main sequence star. What is it called? It is called a red giant. Eventually, the sun will run out of the helium fuel and the hydrogen fuel in the shell, and it will collapse and form a white dwarf. Okay, so that's going to last a really long time. Okay, how long? I don't know exactly, but we're talking like maybe trillion years. I don't know. I don't know the answer. It's a long time. I mean, we're talking. We've never ever seen a white dwarf cool off. There's not enough time in the universe existence, 13.7 billion years. We just haven't had, or 13.8, I guess. 13.8 billion years has not been long enough for any white dwarfs to cool off. So anyway, here we have period of the sun, and now I've got 34. Okay, I think it might be 25, 35. Again, don't worry too much about the exact numbers. It's just super fast at the equator and much slower at the pole. Length of time for a photon that was created inside the core to escape is like 100,000 years, very, very slow. The sunspot cycle is solar max occurs every 11 years, and then the pole reversal occurs. So, and then it takes another 11 years to reverse back. So the total solar magnetic cycle is 22 years. All right. So now would be your time to ask a question. I'm going to look at my YouTube channel. Any YouTubers have questions? Please make sure that you're feeling like you're a part of this thing. And I am not able to see the YouTube channel. Here we go. YouTubers. Any questions, YouTubers? I'm looking. Nobody. Oh, hello. 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 Okay, I put hello again. And I see no questions. So I'm going to assume that you guys are okay. You know what happens when you make an assumption. Never mind. I'm not going to say that. Okay. How you doing? I'm hoping that you guys are okay. If you have questions, please put them in there in the chat or turn on your mic for a second and ask them. Otherwise, I'm just going to move right on. Chapter 11, measuring the stars. How do we measure the stars? Okay, are we looking at the study guide still? Everybody looking at the study guide? Chapter 11. Okay, here we go. The magnitude scale. Okay, super important. Kind of a weird thing, but you know, this guy named Hipparchus invented a system that is backwards. The lower the number, the more, the brighter a star appears, right? The lower the number. And so there's a magnitude scale, and I guess I should just bring that up for a second. Let's bring that up. So the magnitude, when you see it from Earth, is called the apparent magnitude. The magnitude scale is this, the numbers go backwards, and they have very interesting property, which we'll talk about in a few minutes. If you change by one number or two numbers or five numbers, you need to remember what that means about the intensity of the light or the brightness. Another name for intensity is brightness. So there's the apparent magnitude, and then there's this thing called the absolute magnitude, which is the apparent magnitude when you move the star to a distance of 10 parsecs. So it's not the apparent magnitude, it's the apparent magnitude when you move the star. You can't really move it, so it's just a mathematical thing. But in this one, if I ask the question, this is actually what you're supposed to think about. Why are some stars bright? There's really two answers to that question. And what are the answers to the questions? I don't see those terms listed. Oh, well, oh yeah, it's here. Can I just zip down here? The brightness of a star has two things in it, right? It's got the L and it's got the D, right? And you need to know what L is and you need to know what D is. What's L? Who knows what L is? You guys want to chime in? Would it be more fun if you chimed in? Anybody? Anna's the only one who's chiming in so far.
Luminosity?
Luminosity is L, okay, and D stands for?
Distance.
Distance, yay. L for luminosity and D for distance. Okay, so basically this formula is more complicated than you need. You just need to know the L and the D squared. That's the part that you need to know. The 4 pi we don't care about so much. So if I ask you why are some stars bright, you need to know that about half of the stars that are bright are very luminous. They have lots of light coming out of them. So luminosity, if you forgot the term luminosity, L luminosity, where do I have that? It's like a previous chapter, maybe the last chapter. I don't know. I don't know. Where's luminosity? I think I should have put that down as a vocabulary word. Let's write it down. Let's write it down. Let's write it down. You guys know what luminosity is? If not, I'm going to write it down for you right now. You need to know the word luminosity. Luminosity is the total amount of light energy emitted per second. A star, right? The total amount of light energy emitted per second. It is measured in watts, right? Just like light bulbs. That's actually kind of why I tell you that. Because if you think about 60-watt bulbs or 100-watt bulbs or whatever, you know, you already have some experience with them. You know what that means, right? It's brighter to you if you hold it in your hand, of course, right? So if the luminosity is larger, there's more light coming out. If the luminosity is smaller, there's less light. Okay, so I guess there's one more thing I want to write down, and you want to know this idea at least. So even if you don't have to know everything about it, there's this constant. You don't need to know this at all. And then you really need to know It depends on A, capital A, and it depends on capital T to the fourth power. This is the equation for luminosity. It's also called the Stefan-Boltzmann equation. You don't have to know that, but we've already covered it. This is a constant. Don't care. You don't care. Don't worry about it. It's just a number, whatever. This you care about. This is the surface area. So if you have a certain temperature, the more area you have, the more luminosity you have. And the idea is that every square meter of a star is shining with light. So the more of them, the more luminosity, okay? So what is the formula for surface area? Well, because stars are spheres, it's 4 pi r squared. So again, don't care about the 4 pi, but I care about the r squared. If you make a star twice as big, it actually gets 4 times as much area. Okay? I don't think I'm going to be giving you any specific questions on this, but it's an idea that you have to understand. So more area, more light. But look at this, temperature. Temperature is to the 4th power, which means that in terms of which one's more important, the radius or the temperature, you better say temperature. If you make it twice as hot, then you have to raise that to the 4th power. It's 2 times 2 times 2 times 2. You get 16 times as much light. So in fact, in our story about luminosity, the two things are the area and the temp. And which one's more important? This one is first and this one is second. They're both important, but this is first and this is second in terms of their importance, okay? So if you have more temperature or more area or both, you get more luminosity. That's the key. All right, and then the other thing is distance, which we know what is. We know the distance. Distance is the distance. How far away is the star? Okay, so back to the story. Am I on the study guide now? Back to the study guide? I feel like I must be.
You didn't show us the writing close up. We were just seeing the study guide.
What was I going to show you?
I couldn't see what you were writing.
Oh, you couldn't see the writing?
No, because you have it on the study guide.
Oh my goodness. Oh, you failed. Okay. Hold on. All right, hold on. Let me write. Okay, so you just heard me
There,
talking.
now I can see it. Yeah.
Okay. So
Thank you.
luminosity, let's go through it one more time. The total amount of light energy emitted per second measured in watts, capital W. There's an equation here for luminosity called the Stefan-Boltzmann equation. Sigma, you don't care about that. A, you care about, and T, you care about. The surface area is 4 pi r squared. The more area, the more luminosity. T is super important as well because it's raised to the 4th power. So in terms of their importance, temperature is more important and area is next important.
Okay.
Okay?
Yes, thank you.
Okay, sorry about that.
That's okay.
Stop me next time.
You kept talking.
I can't see your writing. Huh? You were trying?
I was trying, but you kept talking.
Oh, that's, my wife complains about that sometimes. I'm trying to tell you a joke and you're not listening. Okay. All right. Okay. Sorry. All right. Back to our share. Okay. Back to the study guide. So about half of the stars, which are bright in our sky, are bright because of their luminosity. And about half of them are bright because they're close. Okay, so absolute magnitude, we'll get back to that again, but it doesn't depend on both, it only depends on the luminosity. So a star which has is a brighter star according to the absolute magnitude is one that is more luminous. That's it. Okay, Cepheid variable, you need to know about that, and you need to know the name of the lady who came up with it. What was her name? Annie? No, sorry, not Annie. Henrietta Swan Leavitt. Okay, where is she? Did I put her down here? Henrietta Swan Leavitt. Oh, I don't see her. Where is she? Okay, you need to know her. Oh, I didn't put her name. Oh, well. But you need to know. She is the one that you talk about. I put Cepheids. I must have. How could I not have asked you to do that? That can't be right. Okay, you're supposed to know this. Oh, man. All right, well, okay, you guys are here, you know. So let me bring up the relationship for you so you can see that. This is a really important relationship, and it's part of the way that we're able to measure the distance to stars. So that's why we want to know about it. Okay, her name was Henrietta Swan Leavitt. And here she is. Actually, I'm going to go ahead and I'll can you guys see her or no?
Yes.
Oh man, it won't let me do slideshow. Okay, slide. Okay, so here she is, Henrietta Swan Leavitt. She studied Cepheid variable stars, and she found this. This is it. This is so cool. Okay, so again, you don't have to do anything mathematical. Just look at what's going on, right? So these stars are called variable stars because they pulse in terms of their brightness. They get brighter and then dimmer, and then brighter and then dimmer. And the time it takes them to do this, the cycle time, is called the period. So you see it's got 1 day, 3 days, 10 days, 30 days. It doesn't have any that are 100 days. So it looks like maybe this is like 50 days or something. Actually, maybe not, 40 days or something like that. Anyways, you don't have to know anything like that. All you need to know is the longer the pulsation period, the higher you go on the luminosity, the more luminous they are. So the longer the period of the pulsation, the greater the luminosity of the star. This turned out to be a really important idea. So on Thursday, when I start lecturing again, I'm going to tell you something really exciting about this. This was because of her ability to graph this data. Another scientist was able to use it to measure the distance to the Andromeda galaxy. It is amazing. It's so important to our final chapters of our class, okay? But anyways, we learned about it here. So the pulsation period, longer period, greater luminosity. That is the Cepheid variable. And Henrietta Swan Leavitt. Okay, and back to this, make it bigger. There we go. Let's see, I've got binary stars. Oh, it's super cool. Okay, and there are 3 ways to see that stars are binaries. You guys are looking at the study guide again? Correct? Okay.
Yes.
All right, so there's 3 ways to tell that stars are binary. There's the really hard way. Visual binaries are, you take pictures of stars and you see them changing little by little over time. They often have periods which might be, more than 50 years, more than 100 years. It's really going to take a long time before you can tell that 2 stars are binary sometimes. The most common method before a few years ago was a technique called spectroscopic binary. It is still very useful, but the way it works is that we look at stars orbiting around each other, and we notice that sometimes the stars are coming towards us, and sometimes the stars are moving away from us. They have, and I'm going to jump to the word right now, they have what is called the radial velocity. So this is also called the radial velocity method, okay, the radial velocity method. And then the final technique is when one star passes in front of another star. It's called an eclipsing binary, okay? So I'm going to go ahead and go to the slideshow and show you guys the pictures for those. And we want to be able to see that, okay? So I'm now on this picture. These are, so astrometric or visual binary. You take a picture and you watch for a while. It's very difficult to do. Spectroscopic binary is much more common. And before a few years ago, this was the only or the best technique for finding binaries. Most of our binaries that we have today are through this method. So when the star is moving towards us or away from us, we get a shift. If a star is moving towards us, we get a blue shift. If a star is moving away from us, we get a red shift. And the amount of the shift tells you how fast the star is moving. So I'll come back to that in just a moment. Okay, the third method is eclipsing binary. And I mentioned that this one was really popular. Right, it has become more popular in recent years. And what you do is you watch the light curve of a star. So in these two techniques, you can't tell that there's two stars there. You just see one star. But if you look at the light, you see very carefully, you notice that there's actually two different spectra. And so one is a spectra for star A, the other for star B, right? Actually, in this case, A would be the one coming towards us, and B is the one moving away from us, okay? And then this third one, we see the light curve for the total, and actually you see a dip. Well, actually, this is wrong, as a matter of fact. So I need to give you a better picture than that. Okay, so let me give you a better picture. Hold on, this is a little bit wrong. So the better picture we found on YouTube, if you look up eclipsing binary. We can go to YouTube. And there we go. We've got a great little video clip here. Okay, and you guys can see this. Okay, so here is the light curve for an eclipsing binary. 30 seconds worth. You can see that one star going behind the other makes it dip a lot, and the other one going behind doesn't make such a big dip. So when do you get a big dip? Pause, right? When the little star went behind the big star. What's the big star? Well, you should identify this as a red giant, and the little star must be a what? A white dwarf would be a good example of this happening. So this is a kind of system that we're really interested in, and we'll talk more about that later. But actually, the little dip occurs when the brighter star, or the star that, sorry, not brighter, the star with the higher temperature goes in front of the cooler star. Okay, so white dwarf is hotter than red giant. So the reason is you're blocking the same area of star, but it's much less light coming out because of the lower temperature. Whereas when the little star is behind, you're blocking that light from a very hot object. So there's much more luminosity coming out of that hotter object. Okay, so this is the picture that you get. There's actually two dips. There's a big dip and there's a little dip. All right. Again, that would have been a good question. Okay, spectral classification. You guys are supposed to remember that. There is a mnemonic, and you might remember that they screwed up the order at first. Well, they just didn't know it. And so Annie Cannon and the Harvard computers are the ones that are going to give us this mnemonic. So Annie Cannon was the lead of analyzing spectra from stars and organizing them and coming up with the spectral classification system. Okay, so they started A, B, C, D, E, F, G, etc., and then they figured out the right order. And the right order is O, B, A, fine, girl, or guy, or anything, kiss me. Okay, and you're supposed to know that the sun is a G2V. Okay, so a couple things there you want to maybe remember. Actually, I'm going to go ahead and do a couple of quick things. Okay. So one thing you're supposed to remember is when you have a binary star system, you have a larger mass and a smaller mass, big M, little m. They are going to orbit a common center of mass. Where is the center of mass location? Okay, is it in the middle?
No,
Not in the middle. Where would it be?
closer to the bigger one.
Closer to the bigger one. Okay, so something like this. That's the center of mass. And the center of mass is the position that these are both orbiting. So the little, the big mass orbits on a little circle. Oh, that's awkward. Okay. And the little mass orbits on a much bigger circle. Okay, yeah. All right, so if the big mass is moving down, the little mass must be moving up much faster away. If the Earth was down here somewhere, then we talked about what we would see. What would happen to the starlight coming from this larger mass? It's going towards us, so it would be blue shifted. And because it's not moving very much, it would be a small blue shift, right? And then this one moving away from us would be a lot faster, right? The speed is small here and much larger here. It's going to be a much larger red shift because of that greater speed. I don't think it makes sense to say small. So, I mean, large, let me put large red shift, small blue shift. I don't know. This is life. Okay. English is not my strong suit. Okay. So, yeah. Okay. Oh, and then back to one more thing. So, oh, be a fine girl, kiss me is the order of the temperature scale. Oh, be a fine girl, kiss me. But if you zoom in to this right here between A and F, in fact, A is 0 is the hottest, and then F0 is over here, and then I guess right in the middle I should put A5. Okay, so A1, A2, A3, A4, right? Goes like that. And so they're getting cooler as you go in this direction. So A9 is the one that's just before you get to F0. Okay, I screwed this up, I think, when I did this with you guys originally, but I'm not screwing it up this time. Okay, my spacing is screwed up, but don't worry about that. Okay, any questions about that? And then the last letter, so G2 is our sun, but the V tells you that it's a main sequence star. Again, you don't have to know that. Just recognize it. You can tell your friends, our sun is the original G2b. Okay, there you go. G2b. Okay, back to the study guide. All right, Harvard computers. Okay, and once you had a classification system, you could create this thing called Hertzsprung-Russell diagram. Let's go ahead and actually flip back to that. And we get our Hertzsprung-Russell diagram. Okay, take a look. Here's our Hertzsprung-Russell diagram. This is a standard diagram. And you can see that there is, most of the stars are here on the main sequence, 90% of the stars. A few are down here, and a few are here, and a few more are up here. What are these ones called over here? Anybody remember? These are the white dwarfs, right? And up here, red giants and red supergiants. Okay, so on a vertical line, you have the same temperature. But as you go up, right, this is very low luminosity. And then as you go higher, more, and then more, right? How could it be that the same temperature has more and then more luminosity? And the answer is what?
More mass.
Not more. Well, that's true, it will, but that's not really the reason why it's more light, though. Why is it more light? Because it has more area. It's larger, right? So small, larger, largest, right? So that's why it's called a red dwarf, a red giant, and a red supergiant. Okay, those would be the names. Okay, if you go along here, the luminosity, right? The higher you go, the greater the luminosity. Along the main sequence, there's a few things to understand, right? Our sun is right here. Right here, it's about 6,000 Kelvin, somewhere here. If you go, and then this is actually, yes, on the main sequence, if you go up or down the main sequence, the thing that's changing is the mass, right? But also the temperature, right? So if you go up the main sequence, it gets hotter. Down the main sequence, it gets cooler. Up the main sequence is more mass. Down the main sequence is less mass. The color of the star changes, right? So the hottest stars are blue and the coolest stars are red. So that's changing too. All right. Those are some of the things you're supposed to know. So main sequence, 90% of the stars, giants, supergiants, white dwarfs. The red dwarfs are on the main sequence, the coolest ones, okay? The lifetime of a star, you're not supposed to know everything, but just a few, right? There's only 3 that I asked you to memorize, and those were the following 3, right? Just have to know 3, okay? So you need to know one solar mass has a lifetime on the main sequence of 10 billion years. That's our sun. How long has it been alive? About 5. It's got another 5 to go. Okay, that's what you need to memorize about the sun. You need to memorize that the smallest mass star that can become a star actually has a main sequence life of 5.5 trillion years. And the largest that we can even, well, there may be some that are larger, but let's just not talk about that. But that we, on this chart, 100 solar masses only lives on the main sequence for 100,000 years, which is kind of crazy. So you need to memorize those numbers. Okay, a life expectancy, we just did that. Okay, turn-off point. Okay, so if you look at a cluster of stars, you find out that not all of the stars are going to appear. And that's an interesting story, right? We actually are going to see something kind of interesting. Let me see if I can bring up one of those. Here we go. I've got one right here. Hold on. Oh, that's what I did wrong. I forgot to look right here. Okay, coming back to the slideshow. Here is a real life cluster, and you guys are supposed to be able to identify, is it a young or an old cluster? And anybody remember how to tell? So the main sequence is missing the upper part. And the reason is the high mass stars have left the main sequence already. So this is an older cluster. The young stars, or not young stars, the smaller mass stars are still there, but the larger mass stars have left the main sequence. Okay, so this is a globular cluster, is an example of that. Globular cluster. Let's see if I can show you. That's a picture of a globular cluster. It has hundreds or thousands of stars, and they are held together by the amount of gravity, and they will never be able to separate from each other. Another kind of cluster you're supposed to know about is called an open cluster, and we'll talk about those in just a few minutes. Okay. All right. Back to the study guide. Okay, metallicity, concept that every generation of stars, they're going to blow up and they're going to produce the next generation of stars, and they enrich the next generation, basically. Okay, I feel like I'm going a little bit slow because I'm supposed to be done with this chapter already. I'm pretty close, pretty close. All right, but a little bit slow. You guys are probably going to go past 5, so. Anyways, so let's see. Anybody have questions so far? We can take a look at our be able to, right? Determine how the brightness of a star changes with distance, right? So the further away you are, the dimmer the star. Oh, actually, I really need to bring up the magnitude scale because I don't know. I didn't talk about it. Let's bring that up. We need to bring it up. I can't ignore it anymore. There's a magnitude scale. Okay, here's our magnitude scale. Hold on, coming up. Here's the magnitude scale, and on the magnitude scale, the brighter something is, the lower the number on the scale will be. The higher something is, the dimmer it will be. You need to memorize a few things, not all these numbers, but you need to memorize this number, 6. This is the highest number magnitude that you can see with a naked eye. After that, you have to use a telescope, okay, or use a camera. You can use a camera as well, okay? The lower you go, the brighter it is, the easier it is to see in the sky. Look at how bright the sun is, like -27. You don't need to know that, but I'm just saying it's really, really bright. So negative means super, super bright. This is apparent magnitude because it's from the Earth, okay? So what you're supposed to know is if you change by one number, where's the math? Oh, I didn't have it in here. I did it on the board. Okay, let's do it on the paper. Magnitude scale. Okay, so you have a magnitude scale. Okay, it doesn't matter where you start, actually, it doesn't really matter. This is the apparent magnitude, m, little m. Apparent. apparent magnitude. Okay, and you've got, like 0, and you've got 1, you got 2, you got 3, etc. Okay, it doesn't matter. Okay, I do need a few more though. 5 and 6. So thanks, Hipparchus. 6 is the number that we use for the brightest, the dimmest star that we can observe with our naked eye. Okay, so what is the difference between magnitude? Which one's brighter? A magnitude 3, or which is brighter? Magnitude brighter, and which is brighter? Which is brighter? Or magnitude 2? Which one's brighter?
2.
2. 2 is brighter, right? And the question is how much brighter? So you need to memorize magnitude 2 is 2.5 times brighter. You need to know this than a magnitude 3. Okay, so if you change by one number, it's 2.5 times brighter. It doesn't matter if it's a 1, it's the same thing, and a 2, or a 5, and a 6, right? It doesn't matter. If you only change by one number, that's the difference in brightness, okay? Which one's brighter, a 3 or a 1? The answer is a 1. Okay, how much brighter? Magnitude 1 is, and you need to memorize. So what's the answer? Okay, it's not 5. What is it? 6.25 times. What is that? That's 2.5 times 2.5. 2.5 squared, right? Times brighter than magnitude 3. Okay, so you need to memorize one number difference, two number difference, and then you're not going to be clear why, but remember the reason why is really easy. Which one's brighter, magnitude 1 or magnitude 6? And the answer is, of course, a 1, right? But the interesting thing is, what is it? It is 2.5. There's 5 steps here, right? 2.5 to the 5th times brighter. And that is 100 times brighter. Okay, so you're going to memorize that. Okay, so it doesn't matter what the numbers are. Okay, so what's brighter? What's 100 times brighter than a magnitude 6? Well, a magnitude 1. What's 100 times brighter than a magnitude 1? What would be 100 times brighter than a magnitude 1?
-6.
Negative 4. Negative 4, right? 5 steps lower. -5. Negative 4 is 100 times brighter than magnitude 1. Okay, so you had to drop by 5 steps. Doesn't matter what the steps were, where you started. Okay, all right. All right, next one. Okay, how do you do parallax? Okay, yeah, you need to know this. Actually, even more in the next chapter, but you need to know the beginnings of this chapter. Okay, take a look at the picture. This is how you do parallax, right? You sit on the earth, you take a picture, right here, started here. Take a picture, and then 6 months later, take another picture, and the star will move, right? If it's close enough to us. And the parallax angle is right here. It's the shift in position from the original, okay? And it's half of this difference, okay? So the star seems to move. And we said this is like holding your thumb in front of your face. Okay, the closer the star is, the greater the parallax will be. A distance of 1 parsec makes a shift of 1 second of arc, okay? And you're supposed to know what a parsec is, right? You guys might not remember, but what is a parsec? Am I on the camera again? Okay, 1 parsec. Right, 1 parsec is a distance for distance that the parallax.
Professor, the slide is on the main camera.
Oh, here we go. Sorry.
Okay, thank you.
Parallax is 1 second right? 1 arc second. Okay, so it's very tiny. The distance that the parallax angle is 1 second, 1 arc second, okay? And 1 parsec, abbreviated PC, right? 1 parsec is 3.26 light years, okay? So actually, just so you know, right, there are no stars that close, right? The nearest star is Proxima Centauri. You don't have to know that, but it happens to be the nearest star. Proxima Centauri is like 4.2 light years away. So if we are on Earth, right, what is the baseline right here, by the way, is 1 AU, 1 AU. The baseline is actually 2 AU. That's how far apart we are making our pictures from, okay? And the bigger the baseline, the more precise you can measure the angle, okay? You don't have to know how all that, but just the basic idea, okay? So what is this angle gonna be, the parallax angle? It's gonna be less than 1 second of arc, okay? Because we're further away. The further away you go, the smaller the parallax angle will become. The closer you are, the bigger the parallax angle becomes. All righty. Yeah, I'm going a little slow. Okay, how does it, oh man, I didn't do this. Okay, determine from a comparison of apparent and absolute magnitudes whether a star is closer or further. Okay, probably the easiest thing is just, again, I'm gonna give you some numbers like this, so I hope you'll know what to do. Let me give you some numbers and show you what I'm talking about. Take a look at the screen, right? There's some different stars here. Here's Sirius, and here's the apparent magnitude, and here's the absolute magnitude. The absolute magnitude is the apparent magnitude when the star is seen from a distance of 10 parsecs, okay? So if you look at this one right here, this is a negative number and this is a positive number. They work in the same way otherwise. So if your absolute magnitude is different by 1 number, the lower one by 1 number, then it's the lower one is 2.5 times as bright, okay? But the reason why absolute magnitude is different is just because of the luminosity. So something with a lower number on the absolute magnitude scale has a greater luminosity. So which one has the greatest luminosity? This one right here, negative 6.69. Which one has the smallest luminosity? And you'd look at this, 4.8. Our sun actually is the least luminous of all these stars. But then here we see apparent magnitude includes the distance and the luminosity together. Okay, so the key idea is if you take a look right here, when you go from negative, actually, I think the funny thing would be, is there any that don't change? They all change. This one's pretty close. No, they're all the same. Okay. If they didn't change, by the way, the reason would be that that star is actually 10 parsecs away. This one is pretty close, right? Pretty close. If it was 10 parsecs away from us, then when we move it to a distance of 10 parsecs, we didn't move it at all. But all the rest of these, what happens is the number changes, right? So why would it be that the number went up? Is it getting brighter or dimmer? And the answer is getting dimmer. We must be moving it away. And the reason is that it's starting at 2.6 parsecs right here. And so if you move it to 10 parsecs, it gets much dimmer. This one is starting at 0.4 and getting bigger, and it also is getting dimmer. And here's why. It's moving it from 3.4 to now 10 parsecs away. 7.7, same thing. Now, how about this one? This one actually is getting brighter. And the reason is it's starting further than 10 parsecs and then moving it to 10 parsecs here. Okay, so that's what you're supposed to get from the absolute and apparent magnitude. Any questions on that? Okay. How do binary stars? I did this already with you guys. Proper motion. Okay, I didn't really describe that, but proper motion is a sideways motion that we can't see. You have to wait for well, we can see it, but we have to wait a long time. Take a picture, 50 years later, take another picture, or 10 years later, something like that. And if it's moved a little bit, we can see the proper motion of the star. Radial velocity we can see because of the Doppler effect. Okay, light curve I did that. I did that. Okay. So I didn't tell you exactly, but when you see the turnoff point, the place on the turnoff point, if you can identify which star is missing, then you know the age of the cluster. Okay, range of human seeing. I did that. I did this. I did this. Okay. I didn't really talk about this, but 1 degree is way too big for parallax. So we have to divide it into 60 arc minutes. Each arc minute is 60 arc seconds, which means 1 degree has 3,600 arc seconds. Blah, 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 blah. Okay, chapter 12, here we go. Interstellar medium literally means what? The stuff between the stars. There's molecular clouds, the coolest. There's H1 clouds, there's H2 clouds, and there are 2 that are missing. Okay, I'm missing 2 words right here. Anybody know the words that are missing? They are called, they're cool. Oh my gosh, they are called, what the heck? Coronal and, oh my gosh. Okay, I'm going too fast. Let me stop. Let me slow down. Slow down, you move too fast. You got to make the morning last. Oh, I see why. Hold on. You guys are still on the slide. That's why. Okay. So what are they called? They are called, oh, wisms. Sorry, I couldn't think of the word. Wisms. Okay. Yeah, that's why I left it out. Okay, so let's find your chapter 12 slides. Bring it up. Okay, these are the slide. These are the types that you want to be able to memorize. Okay, need to memorize these. Okay, here they are. Molecular clouds, H1, H2, WISM, and coronal gas. Okay, so what was important about this? You should know them in order. So you can say which one's the coolest and which one's the hottest, right? So molecular clouds are definitely the coolest. Next up, H1, next H2, and WISM. They're about the same temperature. And then finally get to coronal gases. The other really important thing is, where do you get stars, new stars forming? And the idea was that only the first 3 are good for forming stars. So any place that has enough material, you can form a star. The density is the key to it then. So you can form stars in these first 3, but not in the last 2. Okay, and then the state of the material there, right? Because it's so cold, you actually see molecules, and you're supposed to know how to see them. Now, I actually went and did a little research. I thought he was wrong, that it was only absorption, but it turns out he was right. And it's actually correct to say that there are specific radio frequencies that are being emitted by these clouds, and we associate those with molecules. We may also see absorption, but it turns out it's not as big a deal. It's mostly emission. But these are different frequencies of radio waves that that show us that there's a molecule that's present. And so it comes from, again, you don't need to know that. Never mind. You don't have to worry about it. But any hydrogen that is there must be molecular hydrogen, means 2 hydrogen atoms joined together. Okay, it's very cold. Okay, next one, H1 is neutral atoms of hydrogen, but they're atoms of hydrogen. They're no longer molecules. And what's really important about that is that you're going to get the special kind of radio frequency that is absorbed there, called 21 centimeter absorption. And you may also see emission from that, it turns out. But mainly we saw it, the original radio wave that we saw was through absorption. This is how we see neutral atoms of hydrogen, H1 clouds. And then the H2, the gas of hydrogen is ionized, which means the electron has been ripped off of it or is highly excited. And because of that, it emits light. Okay, when the electron jumps between energy levels, it emits light. So it's pretty hot. And in fact, it's kind of pink or red in color. Okay, WISM, same kind of stuff, hydrogen alpha. And coronal gas is such a high temperature, like 1,000,000 Kelvin, that you actually see X-ray light coming from it. Okay, so let me just skip past the part that you need to, here's H1, okay? And then the mechanism for H1. How does it happen? The electron changes from one spin orientation to the other. So if this is a higher energy state when it's aligned with the proton, when it flips over, it reaches a lower energy state. The way that it does that is by emitting this radio photon. This is a radio photon, but it is a special name called the 21 centimeter line. Okay. Back to the study guide. Okay, I mentioned photoionization. I didn't mention that. So that means that light is causing the electrons to be emitted. Photoionization. Ionization means the electrons leave the atom. Photo means light is what made it happen. Okay, photoionization. So high energy photons hit the atoms of hydrogen and rip the electrons off of it. It's called photoionization. Okay, Herbig-Haro objects are objects that have jets shooting out of them. About half of the protostellar disks are Herbig-Haro objects. CNO we've already covered. Brown dwarf is a failed star. It's a star with less than 0.08 solar masses. Okay, Bok globule is a star. Oh, I skipped past this one. Okay, reflection nebula. Let me just show you a picture of a reflection nebula and then talk about that just a little bit. I think that's the best story. Oh, hold on. Okay, so I'm going to go back to the slide set, show you this picture. This is the Pleiades star cluster. And what you notice is a young cluster, and these stars are very young and hot. And if you look carefully, this is a real HR diagram. There are actually some stars that have left the main sequence, but most of them are still there. But what you see is that some of the smallest mass stars have not made it there yet. And that's supposed to be a sign of a young cluster. So this is not a globular cluster. It's known as an open cluster. And these stars are going to drift apart. So in fact, the Big Dipper is an example of an open cluster. And our sun was once born as a member of a cluster, but we don't see those stars nearby anymore. They've drifted away. So an open cluster is a small number of stars which are not bound together by gravity, which are going to drift apart. If you look right here at the color, the star cluster is passing through a dust cloud, and the light is bouncing off of the dust cloud. It's called a reflection nebula. That's the name, reflection nebula. Okay, Bok globule is the very early collapse of a cloud into a star, and we can't see anything yet. There's no protostellar disk, but in fact, there will be one day. Okay, free fall time is the time needed for a star, a cloud of gas to fall together and form enough pressure to start stopping that fall, start to stop the fall, to resist that fall. And it takes a while depending on your mass. So if you have more mass, the free fall time is short. And if you have less mass, the free fall time is long. It's the time, you could think of it as the time needed to become a main sequence star. It's not exactly, because there's still some, it stops falling freely once the pressure is generated. So once there's a significant protostar, the free fall will stop. It's not going to be in free fall anymore. Okay, jumping down, let's see, I got this. Okay, oh, what's an emission nebula? Something that's glowing with light. H2 regions are emission nebula, and reflection nebula come from the light of the star reflecting off of the gas and dust. Okay, what is the state? What's the relationship? The larger the mass, the shorter the free fall time will be. Okay, describe the reasons for the Herbig-Haro jets. Okay, I did not describe that. Herbig-Haro jets are actually going to be jets that come out of a protoplanetary disk. And what makes them happen? I will go ahead and show you the little picture just to remind you what they look like. About half of the protostars, 50%, are showing these jets. What causes them? Well, the answer is the accretion disk. But that's not the answer, really. There's an accretion disk. I know it has to be there, because I know there's something to form the magnetic field. That's the answer, right? There's two jets, one up north and the other down south. I don't know if it's really a north magnetic pole, but it's either a north or a south, and the other one is the opposite, okay? So Herbig-Haro jets are definitely coming from the magnetic field, conservation of angular momentum, but the rest of it is a little bit confusing. Some of those jets can be moving incredibly fast, okay? So we don't know the exact answer to the question. We just know that it has something to do with magnetic field, okay? Blah, 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 okay, and I kind of showed you the picture already, young versus old. Okay, the minute memorize. The smallest mass red dwarf, 0.08 solar masses. Less than that would be a brown dwarf, unless it's really small, and then you just call it a planet. Okay, any questions? I'm gonna look to see if anybody asks any questions, and if you don't have any questions, I'm moving on. Moving on, I think I'm moving on, and I'll see any questions. I'm looking for the questions. Anybody have questions? Hello, hello, hello. And it looks like there are no questions. Okay, so we are moving on up. Okay, moving to the chapter 13. I'm definitely behind. Okay, so we have stars blowing up, and stars blow up in different ways, and you're supposed to know how that works. I'm just going too slow. Okay, keep on moving. Okay, here we go. What is a type 2 supernova? Type 2 supernova is a star which is greater than 8 solar masses, and it goes all the way to iron. Okay, you need to know that. A star that goes all the way to iron will give a type 2 supernova, and it has to have a mass greater than 8 solar masses. Okay. Hydrogen shell burning is the stage after the main sequence when the core begins to collapse, not collapse, contract. Let me use that word, contract. The helium core begins to contract, and then the layer right outside that becomes hot enough to fuse the hydrogen. You get hydrogen shell burning, and that's really the beginning of the red giant phase. And then a little bit later, the helium will ignite as well, causing even more energy to be pumping out. And we call that the helium flash. What will happen? You get a red giant. A red giant is, let me just talk to you guys. I'm going to stop my share. So a red giant is a stage when the star is very large. And it is so large, in fact, actually what's going to happen is our sun is going to eat Mercury and Venus and eventually even eat the Earth. It's not going to eat Mars, but it's going to be huge, right? And the layers of the star that are very far away are not held very strongly by gravity. So every time the star pulses with energy, it'll blow away a bubble of material. And this material will eventually become what is called a planetary nebula. So if a star is all by itself, just by itself, you could probably see a spherical shells of material being blown away. And supposedly, the star, like our sun, will blow away 70 to 80% of its mass, until the only thing left is really the core. Okay. Otherwise, actually, as it expands and starts to eat its planets, as it eats the planets will stir its interior, and it'll get kind of an interesting shape to it. That's one of the ways that it might get an interesting shape for its planetary nebula. Another would be if it has a companion star, then that could also cause it to be to change its shape a little bit, and not just be spherical, but have like these stretched out lobes, north and south and sideways. Okay, back to the thing. Yeah, helium flash planetary. Okay, Messier objects. Charles Messier, comet hunter, had a list of objects that he thought were comets, but they weren't comets. They were in fact objects that are not comets, right? So what else would they be? They are called the Messier objects now. And what they are is things that he couldn't tell with his little telescope, how beautiful they are. So this is a picture of a planetary nebula. Let's go ahead and, sorry. Let me go ahead and make it big. Okay, planetary nebula. And the reason it's shining is that the last little bit of the star has collapsed, the core has collapsed, And now there's a white dwarf in the middle that's shining. It's really hot, shining with ultraviolet light. And so it's exciting, these stars. It turns out, I said at 500 years, it may be as much as 10,000 years, but it's going to be a short while. It's not going to last very long. Okay. Here's Charles Messier, and he found all of these things that he thought were comets, but they didn't move. And so he started to keep track of them, and he made a star chart showing the locations of these, and he shared it with other astronomers. So they are actually amateur astronomers' friends. And here's the first one. It's called M1, and they're numbered according to the M. The M number, M with a number is a Messier object. There's all kinds of famous ones. There's the Pleiades clusters, M45. There's the Andromeda Galaxy, M31. There's the Beehive cluster, M44. There's, there's so many famous, M57 right here, the Ring Nebula. So each one is kind of a cool special thing. There's 110 of them now. And he just didn't have a telescope with high enough resolution to see the detail. So they are planetary nebula, they are supernova remnants, they are star clusters, and they are galaxies. Okay, so we will learn more about galaxies after exam 3. Okay, back to our study guide. Okay. The Roche lobe. Okay, I guess I'm going back to the PowerPoint again because it's probably the best way to show you the Roche lobe. Here's our Roche lobe, right? We have red giant white dwarf companion. It's a very common thing. The red giant is spewing out material. If that material falls past this point, past the Roche lobe, then it will now be eaten by the white dwarf. And what happens when that matter falls in and hits the white dwarf? Before it falls in, by the way, it'll accrete. It'll be in the accretion disk and get really hot, which gives it jets of magnetic field. But then it will fall onto the surface of the white dwarf, where it will fuse very quickly, and we get what is called a nova. So every time you dump material onto the white dwarf, you get a nova, 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 nova. It can happen over and over and over again until you reach what is called the Chandrasekhar limit. So we will need to review that. Let's go back to our study guide though. Okay, we've got Roche. Oh, Chandrasekhar limit was next. Okay, so it turns out that the white dwarf has a limit in how big it can be, and that's called the Chandrasekhar limit. The number is 1.4 solar masses, 1.4 solar masses, okay? And so if the red giant gives just a little bit too much mass, then the Chandrasekhar limit is going to be exceeded and the star will blow up. And when a white dwarf blows up, it is called a type 1a supernova, okay? There's two terms here, electron degeneracy pressure, and neutron degeneracy pressure. Let me go ahead and make sure you remember. What is electron degeneracy pressure? And actually, you know what? I feel like I don't need to tell you this. You guys already have this in your notes. I'm just saying there's too much stuff. I'm never going to finish. Let me go back to the study guide and just say it out loud. This is the force which stops a white dwarf from collapsing right here. What is the force that stops a white dwarf from collapsing? Electron degeneracy pressure. What is the neutron degeneracy pressure? The force which stops a neutron star from collapsing. Okay. Weak nuclear force we described already is it explains why a neutron can fall apart, but also how a neutron can be formed, how a neutron star can be formed. Stellar ejecta is just something that gets spewed out of an exploding star. Thermonuclear runaway is what's going to happen in a type 1a supernova. Supernova light curve. Why did I put that up there? It's what we watch. Okay. Okay. I have nothing. I have a picture. That's all I have. I have a picture. Okay, supernova light curve. Here's a supernova light curve. Okay. Supernova light curve. Okay, supernova light curve. There we go, supernova light curve. It gets brighter and then it gets dimmer. And if you watch the whole thing, you can figure out the mass of the star that exploded. So this is actually a pretty big deal. Now, type 1a supernovas are always the same mass. So we're going to be learning that they are one of our best standard candles. which means we know how bright they should be. And so when we see their brightness, we can compare that. We know their absolute magnitudes. We compare that to the apparent magnitude, and we can measure the distance. Okay, so that's the supernova light curve. And that's why we watch it. A neutron star, going to talk about that. Gravitational wave and kilonova. Okay, neutron star. Let's talk about neutron star. So a star that is more massive will go all the way to type 2 supernova. And the reason it does a type 2 supernova is it's trying to burn iron. And so iron, unfortunately, when you fuse iron, it does not release energy, it absorbs energy. So when you start to try to fuse iron in the core, you actually immediately collapse and the star explodes in a type 2 supernova. And actually the first one that we ever saw was Messier 1, M1, the Crab Nebula. And as we watched it, we noticed that it got bigger. And that's a kind of a cool story because they were able to calculate when they thought it was born. And when they looked back in the Chinese astronomical record, they found in the year 1054, there was a guest star. And it was visible for 3 weeks during the day and for 2 years at night. And so we finally knew that stars could die and explode and then lead to this explosion that we see is called the Crab Nebula. Okay, so I kind of alluded to this, right? When it's very large, gravity is not strong enough. Any pulses will pulse matter away. And then at the very end, when the core collapses and forms a white dwarf, so this is going to be mainly, okay, the planetary nebula is not a large mass star. It's less than 8 solar masses. It's not a type 2 supernova. Okay, and blah, blah, blah. Okay. So now, what happens if you go all the way to iron? I'll go ahead and stop my share. What happens if you go all the way to iron and you have between 1.4 and 2.7 solar masses, right? Well, you can't form a white dwarf anymore, right? There's too much mass. So what happens is the protons that are making up the nuclei and the electrons are going to be forced together. The electrons will be forced into the nucleus. And so what you get is a neutron, right? A ball of neutron. So what you get is a really tiny little object, right? Remember how tiny it is, called a neutron star. So this has a mass in this range, which is 10 miles or about 20 kilometers, 16 kilometers, about 20 kilometers across. It's the size of a small city. And it has this much mass, right? It's huge, okay? So we talked about that, and I mentioned that the Earth would shrink down to the size of a bowling ball at this same density, okay? All right, so study guide, okay. Why do we only see a small number of pulsars? I didn't really talk to you guys too much about that, but the only way to see a pulsar, what's a pulsar? Is a rapidly rotating neutron star. And so the neutron star is rotating, and the pulse of light and energy shines at us. We see it, but it's just kind of an accident almost if it shines at us. So most of the ones that are out there are probably just not shining at us, so we can't see them. So we only see a few. What happened on August 17, 2017 that has changed astronomy forever? And I need to stop for a second and tell you what that is. Okay, if you don't know what that is, you haven't watched the video, and you're going to get these 2 questions wrong. But this is a big deal. This is incredibly amazing. It's called the kilonova. It was the first one we had ever seen. It was the merger of 2 neutron stars. And this is amazing, because we discovered that we were wrong about where all the elements come from. That neutron stars actually give us most of the heavy elements. Most of the heavy elements. I think I probably should have talked to you about this, but you know, this is the review, so I could probably talk to you for just a second right now. Let me show you a page that you could look at if you want to know more. Called stellar nucleosynthesis. And switching here. I'm going to show you this page, stellar nucleosynthesis. I'm going to go to the Wikipedia page. There's our PP chain, there's our CNO cycle, and our sun is more PP than CNO, but as you increase the temperature of the core, you start doing more CNO. And you blah, blah, blah. Here we go. Here's our periodic table. Can everybody see the periodic table? I'm gonna, right here, shake your head. Okay, good, good, good. Okay. So Big Bang produced hydrogen and helium and a little tiny bit of lithium. Okay, that's the main elements that came out of the Big Bang. Why do all stars begin with hydrogen burning in the core, main sequence? Because that's the most abundant element in the universe. Okay, dying low mass, exploding massive stars. That's type 2 supernova. Look at all the gold, right? That's lots of cool stuff. But actually, the heavier elements are purple. And we didn't know this before 2017. We didn't know it. We suspected it, by the way. I didn't know that, though. And so merging neutron stars. Au is the element gold. PT is platinum, iridium, rhodium, silver, uranium, thorium. There's a whole bunch of other things down here as well. And you notice how purple they are. That's where the bulk of the gold in your jewelry comes from, right? Here's a type 1A supernova, which also makes stuff, right? It's kind of cool to see that. There's other things too, but those are the ones that you need to really understand, okay? So that's kind of an important idea. Okay, back to the study guide. Chandrasekhar limit, memorize that. Memorize that. Okay, so small, medium, large. Okay, why is this small? It does not go all the way to iron. So it will die as a white dwarf. You'll get a white dwarf. A medium, between 8 and 20, still pretty close to the right answer. It dies in a type 2 supernova, and the core becomes a neutron star. Large stars, right, are going to have masses greater than 2.7 solar masses, and they're going to be, this should be 2.7, not 3. This should be 2.7, not 3. That's a mistake. I've changed it, but I forgot to upload the new study guide, sorry. Okay. And large, the core is greater than 2.7, you get a black hole. Okay, black hole. All right, I'm done with the chapter. I'm moving on. If you have questions, make sure you ask them now because I'm moving on. Okay, this is going to be an abbreviated version because I don't want to keep this going more than a half an hour. But I will go ahead and continue and finish chapter 14, important ideas. Okay, important ideas for chapter 14. I'm looking for questions. Any questions? I'm looking for your questions. And I can't see them because I'm messing up. Okay, hold on. Any questions? I'm looking for your questions and nobody's got questions. Okay, so if you have questions, be sure to ask them and then I will answer them. And then we're still gonna do, oh my gosh, I'm gonna do those numbers. I'm gonna go super fast, okay. Let me take a drink of water, 1 second. Okay, so where are we here? Here we go. Okay, am I still on the study guide? Study guide? Okay, study guide. Chapter 14, super fast, black hole. That is something that has so much mass that not even gravity, gravity is so profound that the matter shrinks down to a mathematical singularity. Ugly, the mathematical point. We'll talk about that. Special relativity, things going fast. General relativity, large mass or large acceleration. Muon, a high energy particle, not a high energy particle, a particle created in the upper atmosphere from a cosmic ray hitting it. Cosmic ray is a particle coming from another star or a supernova from another place in the galaxy or even another galaxy, and a high energy particle. They're moving near the speed of light. A muon is also going to move near the speed of light. It's created in the upper atmosphere of the Earth. Reference frame, how you are looking at the world. And we're going to talk about the relative velocity, right? A pretty important idea. How fast is the other frame moving relative to you? And the 3 effects of special relativity are, I don't see it. I see time dilation. Oh, I left it out. Length contraction. and relativistic mass. Okay, so actually, let me stop. Let me show you what you need to know. 3 ideas. Okay, Kelly Malone. Okay, that was her scratch paper. Here we go. Flip it over. Use another one. Here we go. All right, special relativity. Special relativity is the idea that there is a stationary observer. Maybe the Earth would be the stationary observer. And then there is a moving observer. Okay, maybe a rocket. Ooh, that's a different rocket than I usually draw. Okay, this person is here. Okay, and they're moving with a high speed, v. Okay, whatever. Okay, and so these are 2 inertial reference frames if they're moving with a constant velocity. Okay, now if I was on the rocket, would I be moving? And the answer is no. I would see the Earth moving backwards at this speed v. Okay, that's important for you to understand. That's called relative velocity. Okay, but we're going to go ahead and want to remind you that the reason we know that the rocket is moving is because they have to accelerate to get up to speed, and the Earth never feels anything. Okay, so there are 2 postulates. You need to know the 2 postulates. These are the 2 assumptions. If one of them is wrong, then everything is wrong, but they're not. But there are 2 postulates. Number 1, the laws of physics are the same for all inertial reference frames. And that means moving at a constant velocity, right? Inertial reference frame. Okay, the laws of physics are the same. So if I do an experiment, I can't actually tell that I'm moving at a high speed. You can be on this rocket and feel completely normal. You can't tell that you're moving or you're standing still. It doesn't matter. The laws of physics will work. Number 2, the speed of light is the same for all inertial reference frames. And you'll measure it the same, okay? So it doesn't matter who's making the light. All that matters is the person who sees the light will see it moving at the speed of light, no faster, right? Speed of light is the same in a vacuum, all right? In a vacuum, I don't have to tell you that because I never talked about anything but that, but in a vacuum. But anyways, don't worry about that. Okay, so what are the 3 things that you need to know about special relativity, right? 3 things. Number 1, time dilation, right? Time passes slower on the rocket, according to somebody on the Earth. There's an equation, T equals gamma T0, but we're not going to do any math in this class. I just wanted to show it to you. This T0 is the time on the rocket is called the proper time. It's the time where you're doing the experiment, okay? Proper time is T0, okay? Number 2 is length contraction. And if the rocket happens to be going to a star, right, and you measure the distance to the star in the frame of reference of the Earth, then that's called L0. It's called the proper length. And if you look at the length, the distance when you're in the rocket ship, it turns out that the rocket sees the distance as L. Of course, the rocket doesn't think it's moving. It thinks the star is coming towards it. But when they ask the question, how far away is the star? They're going to see the length as L. And the length contraction is that the L that as seen by the rocket is L0 divided by gamma. It's smaller length contraction. And the last one is called relativistic mass. Relativistic mass. And E, so E, let me write down the full equation. E equals mc squared. And this m is actually gamma times m0. So m0 is called the rest mass. And the faster you go, the larger this factor gamma becomes. Okay, I know I left all of this stuff out. Hopefully you took some notes. But gamma is the thing that controls how it changes, okay? So the faster you go, the bigger gamma becomes. So the faster you go, the more mass you will have, because mass is a kind of energy. So the more energy you have, the more mass you have. So it turns out something bad happens if you try to go the speed of light, right? If V equals C, then gamma equals infinity, and that's not possible. So one of the things that happens is matter must not move at V equals C. That's not possible. It's not possible. You can't go the speed of light, okay? All right, so the faster you go, the more mass you have. All right, so those are the three ideas of special relativity. And then we have general relativity, and you only need a few ideas here too. Okay, so I'm just going to give you the quick version. Okay, space-time is flat when there's no matter there. But when you have matter, it gets curved, right? And the curvature depends on the amount of matter. Okay, matter curves space-time, right? It curves it, right? So it warps it, Okay, I don't know how to draw that. I'm lame. Okay, sorry. I'm gonna cheat. I'm gonna just show you a picture. Okay, can I do that? Trying to find a picture here. Here, let's find a picture. Space-time curvature. Oh, that's what I want. Man, that's so much easier than trying to draw. Okay. I can't draw very well. So here we go. Take a look. This is an example right here. The Earth is curving space-time. Black holes make an extreme curvature, right? And actually, this is a really great picture. Oh, I really like this picture a lot because it's three-dimensional, right? It shows you that this is all, the pictures over here are two-dimensional, but this is reality. It's really a three-dimensional picture. The greater the mass, the greater the curvature will be. So when you concentrate the mass, the curvature also gets stronger. And this is actually showing you an orbit. This is an orbit of like a planet orbiting the sun, for example. And so, yeah, anyways, one of the effects of special relativity is that light is even bent by, general relativity is that light is even bent by space-time. Okay. So anyways, general relativity is either large gravitational fields or large acceleration. Okay, so that's when you need to use general relativity. Okay, that's when you use it. Okay, what are the big things that you get, the big results, the main effects? General relativity. There's two big effects. Okay, two big effects. There is also a this is going to be like, I'll call it gravitational time dilation. And then the other one is gravitational redshift. Okay, so it turns out you don't have to have a black hole to do this. You could do this with anything, even the Earth, right? But actually, black holes are more interesting. So let's do a black hole. Let's do a black hole. Okay, there's a black hole. Now, is there actually a boundary to a black hole? This is a black hole. There is no actual boundary. In fact, at the very center is supposed to be a singularity. That's the name for it, singularity. And if you like black holes and you want to learn more about it, you should take another course called Black Holes in the Universe. Okay, singularity is a mathematical point, but there is this certain ring here. It's actually a sphere that I'm going to call the event horizon. And you need to know that name, the event horizon, and why it's special. Another name for it is the Schwarzschild radius. Schwarz. How do you spell Schwarzschild? Schwarzschild radius. And it's a mathematical place, right? It turns out that if you want to get away from a black hole, you need to have a velocity called the escape velocity, right? And as you get closer, the escape velocity gets bigger and bigger and bigger. And when you get to this point, when you're on this ring called or it's not a ring, sphere, called the event horizon, the escape velocity is the speed of light. So since nothing can go the speed of light, nothing can go faster than the speed of light for sure, but the only thing that can go the speed of light is light, that at this point, not even light can escape from the black hole. And so you can't see a black hole, right? The singularity is hidden behind this event horizon. There are no naked singularities. You can't see them, okay? So it's black because light is captured, right? Light is captured. Okay, now, it turns out that if you're outside, the light can get away, right? The light, a photon, could get away. And actually, I'll tell you about the two effects that you need to know. Okay, so if you talk about clocks, there's a clock, clock A, which is far away from the black hole, and clock B, which is near the black hole, right? What's going to happen to the clock? The clock that is closer to the black hole is going to tick slower. The clock that is closer in the more, so the greater the gravitational field or acceleration, the slower the clock will tick. Okay, and so which clock ticks slower? B, because it's closer. If you watch from A, you'll see B ticking slower. If you watch from B, you'll see A ticking faster. They will actually agree with each other, right? They are going to agree. They're going to see the same thing, right? So when B looks out, they see this clock ticking faster. When A looks in, they see this clock ticking slower. A photon escaping is going to do something interesting. It's going to have this frequency when it started, call it F0, and then it has a frequency when you finally see it. Let's put an eye out here, right, that sees the photon coming out, right? And they see a frequency F. And the frequency that you see is less than the frequency that was emitted, okay? And this is called this is a red shift, right? The red shift, that the light appears to have a lower frequency. So escaping from the black hole comes with a cost, right? You lose some of your energy, or it looks like you lose your energy, and the photon has a lower frequency when it comes out. That's the gravitational redshift, okay? So another thing you're supposed to know is if somebody were to fall in to a black hole, I don't know why they would do that, but let's say they did, right? Let's make them fall in feet first, right? And then here's an astronaut falling in feet first. I don't know what happened to their arms. I can't draw arms, so that's why. If they fall in feet first, what happens? The force of gravity is stronger on their feet than on their head. And what it has what happens is it stretches them. So it's called the tidal force. And then what's the name that we give for somebody who's falling into a black hole? The tidal force is called spaghettification. Spaghettification is the technical term, right? You are stretched into a strand of spaghetti. If the tidal forces near a black hole are extreme. Okay, tidal forces are extreme. Okay, so those are some of the biggest ideas. So can you see a black hole? The answer is no. But you might have heard that they just recently took a picture of the first black hole, huh? Wait a second, how do you do that? And I didn't put that in the study guide. I probably should have, but I didn't, so don't worry about it. There's too many things to do anyways. First black hole picture. Okay, this is the first black hole picture. It has never been visualized before, okay? And I'm not showing you yet. I'm about to show you, hold on. Let's take a look of the first black hole pictures, okay? And I like this one a lot. This is a really awesome picture. It is not a black hole picture though, right? What is it the picture of? Well, this ring of material, I don't want to hear you. This ring of material around the black hole, not the black hole itself. The black hole is actually inside of this dark ring right here. And I'm not going to do this with you. You can read this yourself. Okay. But anyways, what's important? A black hole cannot be seen, but if a black hole happens to be feeding, then something interesting happens, right? If matter comes in, maybe from a nearby star or whatever. But anyways, the matter will go into orbit for a little while and form a disk of material. And so as it falls in, the gravitational potential energy will heat it up and it will get very hot, right? And it's called an accretion disk. Okay. And it's temporarily orbiting the black hole before it eventually gets eaten and actually goes into the black hole. But it's very hot. We're talking like 100,000 Kelvin, which means it emits X-ray light. Okay, in fact, that was the way that we saw our first black hole. We turned on an X-ray camera and saw X-ray light coming from a place called Cygnus X1. Okay, you don't have to know that either. Okay, back to our study guide. I've jumped around, but I'm trying to show you all the things that are in there. So let's just make sure we hit it. Special relativity. We didn't talk about the muon. I'll come back to that. I'll tell you these two right now. I'll tell you that. It's a little story. Talked about reference frame, velocity, time dilation, length contraction, rest mass, and the how the mass changes with speed. I did not talk about this. I talked about the singularity. I talked about the event horizon. I talked about space. I kind of just mentioned it. That was the stuff that's getting warped. I talked about tidal forces, spaghettification, gravitational redshift. I didn't talk about supermassive black hole. Okay, so, and I didn't talk about gravitational lensing. So let me come back and tell you this story, and then this, and then I'll jump down here. Okay, and then we're almost done. Okay, and I will then give you the 10 questions for the exam. Okay, so what happens is, here's the Earth, right? Earth. And in the upper atmosphere, these very high energy particles called cosmic rays hit the surface of the Earth, and the energy is absorbed by the atmosphere. And then it creates sometimes these little things called muons, okay? And they're going to be moving at like 99%, 0.99 C, something like that, really, really fast. Now, they're only supposed to live for 2.2 microseconds or something like that, very small amount of time before they decay. And so if you do the calculation, even if they're moving near the speed of light and you don't use relativity, you find out that they never get very far. They pretty much die by here, okay? They're dead by here, okay? If you don't take special relativity into account, they could never make it down to the surface of the Earth. But because of their incredibly large speed, the gamma is like, it's like 5 to 10, right? It's huge. And as a result of that, instead of making it 1/5 of the way, they really can make it down or even further, but of course they hit the surface of the Earth. And so what it turns out, we see the muons live much longer. This is going to be the T0, the proper time, right? If you could hold one in your hand, this is how long it would live. But because we see them moving, they live 5 times as long or even 10 times as long. And therefore, they make it to the surface. And I don't have time to tell you, but their muon detectors are being used right now by archaeologists inside of the pyramids in Egypt to see if they're secret rooms. Okay, that's a pretty cool side fact. Okay, so I talked about cosmic ray, cosmic beam. Okay, muon. Inside of the center of every galaxy center, what do you have? We're going to talk more about this. A super massive black hole. And we're talking big, right? We're talking the one inside of the Milky Way, you're going to need to know, not this chapter, but next chapter, is 4 million times the mass of the sun. It's huge, right? And so these things are incredible. We don't even really know how they form, but the center of every galaxy, so if I draw a spiral galaxy what you want to know is in the center of that spiral galaxy is a giant black hole. And so what's really cool is that if we're here on the Earth, we're just minding our own business on the Earth here, and we look at this galaxy, what if there's another galaxy really far away behind it? Can we see it? And in normal physics, the answer would be no. But something amazing happens, right? If the light that would never have normally have hit the Earth goes right past this giant galaxy here, something happens because of the gravity. Light is bent by gravity. That's actually one of the things that special relativity told us. And then the light actually bends over and hits the Earth. So it looks to our eye as though the galaxy is over here, right? We see the galaxy as being here, but in fact, it's behind the black hole. And what's really crazy is that the light could come this way and doesn't go straight, is actually bent to the Earth this direction. And so we see the galaxy here as well. We see twin galaxies. They're identical. And it's like, that's not possible. The universe would not play that trick on us. So this effect where the galaxy bends the light almost like a lens, like a big magnifying glass, is called gravitational lensing. And it is amazing and something like super crazy. If a supernova goes off, we'll see it, and you might actually see it go off first in this version of the galaxy, and then later in this version of the galaxy. It means that it wasn't exactly centered. It was maybe slightly higher. It didn't go quite as far this way, and it had to go further this way. And we actually see that happening later. Okay, so that's something important to know about. Supermassive black holes, gravitational lensing. The last thing I want to tell you, and this is actually, I think we're pretty much done with the material, I hope. We'll check. You're not supposed to know that. Okay, skip that. Okay. Is what happens if two black holes are orbiting each other, right? And the answer is they make ripples in space-time, and those ripples are called gravitational waves. And waves are energy. Sorry about that, my lights went out. Gravitational waves, which are a kind of energy. Something happens then as they orbit each other, they start to spiral closer together, and they will eventually merge. And so that's actually a brand new part of physics we have, which is called GWO, and LIGO is one of them. It's a gravitational wave observatory. It's a new kind of astronomy, and it has only been around for 5 years. Okay, this is LIGO, is one of the versions of them, and in a few years we'll have LISA. LISA is coming. Don't worry about that. But anyways, it's kind of exciting. This is really exciting, super exciting, and I don't have time to tell you how excited I am. I want to tell you, but I don't have time. Okay, let's check back with our study guide and make sure we've hit everything, and then I'll do the questions with you. Okay, supermassive. Okay, I think I got everything. Postulates. Okay, what's the twin paradox? We did this in class. Let me remind you. If you are on the Earth looking at a rocket, you see the rocket moving. But if you're on the rocket, you see the Earth moving. That's a paradox because we can't tell who's moving. So if one twin gets on the rocket and the other twin stays on Earth, the twin that is moving will appear to age less than the twin that is not moving. But I just told you there's a paradox, right? You can't, if you just see the two rockets moving, you can't tell which one's moving. The paradox is not a paradox, however, because only the rocket feels an acceleration. And so if one day when this happens, if one twin stays behind, they will age more than the twin that goes on the rocket ship. Okay, I talked about the edge of the black hole, the event horizon. I didn't do this. What happens if you drop a flashing laser into a black hole? The laser would appear to blink. So if it blinks every second, right? Then as it drops, the seconds are going to be dilated. We're going to see the flashing slower and slower and slower. and the color of the light will be red shifted. And eventually we won't see it anymore because it'll be shifted into the infrared. Okay, explain how we know. This is really something, I don't know why I put it on here because I messed up. It's really something we don't have to worry about until the next chapter. But we see evidence of supermassive black hole because it causes stars nearby to orbit. And we'll talk about that next chapter. Okay, I already talked about this. We don't see the black holes, we see the accretion disk. Okay, I am done with the review. And what I'm gonna do right now is take a breath. Thank you guys for sticking with me. And then for the last couple minutes, if you guys are done, we're done. That's the review of the material. Was that better than the recorded session? I don't know why does this feel like it was anything better? I don't know.
I like it better because I could ask you questions.
You have a chance to ask questions. Okay, you didn't ask any, but, or you asked one. Okay, one question. But anyways, okay, one is better than none. Okay, so the last thing would be, I will go over, and that would be the reason to do it because I could talk about the questions that will be on your final, not your final, your exam 3. Give me 1 minute to bring that up. Okay, spring 2020, exam 3 preview questions. Okay, and here we are. Okay, if you guys are ready, here is the first question. Question number 1. Let's see. What type of light is most likely to be detected from the material falling into a stellar mass black hole? So the reason that you're going to detect it is it's going to get very hot. And what type of light? So the answer is the way that we see this currently is with the X-ray part of the spectrum. Okay. Now they will emit visible and infrared and microwave, but it turns out the X-ray is the signal, right? We're not going to notice it. I don't know why. I don't know why. It shows up bright in the X-ray. That's the answer. Okay, that's the answer. I don't have time to debate it. That's it. Okay, one possible explanation, and it's not the only one, it's just one, for the weird, beautiful, fantastic shapes of planetary nebula, is that they swallowed some of their planets, which then stirred their interiors. Now, this is somewhat, no, that's not true. Never mind. This is not true. This is somewhat true, and this does actually cause some of the material to be flung away. But that wouldn't create the weird wonderful. It would make like a ring. Okay, that makes a ring shape. And it's, I mean, this would be extremely rare. I don't even think this is possible. Okay, so I think this is the answer. This is the answer, okay? Okay, figure below. I already told you it was going to be on here and I'm showing it to you. All right, well, make sure you know it. So what is the arrows that are bouncing around? What would those be? Those would be photons. See if I give you this picture again and I say, what's Y? Even though I don't have a letter Y. That's a photon. What is the particles that are shooting right out of the sun? Gamma rays, neutrons, positrons, photons, neutrinos. And everybody remember the neutrinos? Yes, very good. Neutrinos. Okay.
I have the questions already.
Oh, you already got them? Ah, good for you. No problem. You're gonna do this. Is gonna be your best test ever, right?
Yeah, with Liz.
You're gonna get the best grade ever. Okay, here we go. Question number 4. And remember the video is being recorded on YouTube. So if I'm going too fast, don't worry, you just go back and watch the recording, okay? All right, number 4, 2 very precise clocks are synchronized together at sea level. Can you guys record the Zoom sessions? I think you can too, but whatever. You don't have to. 2 very precise clocks are synchronized together at sea level. Clock A is kept at sea level and clock B is taken to the top of Mount Everest. So before we go any further, do you guys know anything about gravity? Is gravity the same at sea level and on the top of Mount Everest? The same or different?
Slightly different.
Slightly different. Is it greater or less when you go to the top of a mountain? It's a little bit smaller, a little bit less, right? Because you're further away from the center of the Earth. Remember, the distance between you and the Earth is what determines the force of gravity. Okay, so if you have a little less gravity, what should happen? The clock should tick a little faster, right? So clock B at the top of Mount Everest is going to tick a little faster. Clock A will tick a little slower. Okay, so you take clock B up to sea level, clock B up to Mount Everest for a year, then bring it back, and you compare the clocks. So the two clocks will still be synchronized? Nope. Clock A will be behind clock B. Yes, that's true. It'll be slower, right? And then clock A will be slightly ahead. Nope. Clock B will be behind, which is the same thing as C, which is still wrong. Okay, so answer is B. Clock A will be behind clock A. Sorry, let me read it again. Clock A will be running behind clock B because it has been running slower. Everybody good?
Yes.
Okay. Okay, here we go. An example of magnitude. If star A has an apparent magnitude of 8 and star B has an apparent magnitude of 13, which one is brighter? 8 or 13? So the answer is 8 is brighter, and it's 5 magnitudes brighter. 5 magnitude numbers. So if you remember what that means, it's 100 times brighter. 100 times brighter. 5 magnitude numbers means 100 times brighter. Star A, 8, is 100 times brighter than star B, magnitude 13. All right. Why does stellar fusion of massive stars end with an iron core? What happens when you try to fuse iron? And the answer is the core becomes so hot. No, that's wrong. Iron cannot undergo fusion. That's wrong. Iron requires such a high temperature that it does not occur. Yes, it does. It occurs. But this is the answer. Iron does not release energy when it undergoes fusion. And so that causes the star to collapse and then explode in a type 2 supernova. All right, next question. Here are 2 questions. Both of these questions are using the chart here, question 7 and question 8. So use the chart below. Hint, the first letter of the spectral class is most important. So there's A, there's B, A, M, A. Remember the letters? O, B, A, F, G, K, M. O, be a fine girl, kiss me, okay? From the data given, which star has the greatest surface temperature? And so the answer was O, but there's no O. So the next letter, B, is the next hottest star. So HR 4621 is going to be the hottest. Make sure you look for the answer, not the letter, because the letters are going to be scrambled. Okay, the test version that you get will not have the order of the answers the same as the ones here. It will be scrambled. Everybody gets a different scramble, by the way. Isn't that crazy? Oh my gosh. All right, so everybody knows the answer, right? So the answer is O, B is the hottest, A is the next, A, and then M would be the coolest, right? Because kiss me, M is the last letter. From the data given, which star in the table would appear the faintest in the night sky? Well, so in the night sky, faintest, I'm talking about the apparent magnitude, right? So we're looking for which one of these stars is the dimmest star. And the way the magnitude scale works is the higher the number is, the dimmer it is. So this is the highest number. This is the answer to the question. 65 tau is the dimmest star that I would see. Can I see it? Can I see a magnitude 4? Because you may get a question, can I see all of these stars? And you have to remember that if it's bigger than a 6, you can't even see it. 7, 8, 9, 10, 11, 12, I can't see that, okay? Here we go, jumping down, question 9. Which kind of interstellar medium is primarily photoionized and emits H-alpha radiation? This is visible light, I can see it. So the answer is not H1, which is cold, and you can only see the 21 centimeter radio waves, not coronal gas, which is incredibly hot, and you can see only X-rays, or you see X-rays. The answer is H2 regions, okay? If it was molecular clouds, it would be radio waves, but molecular spectra, radio waves. Okay, last question, and in some respects, this is very tricky because it is a multiple response question. Oh, that reminds me, I make sure that's what I forgot to do. You have to select all of the answers that are correct. Okay, so which of the following stellar properties increases as you follow the main sequence from the right side to the left side? Now, I really think it's important that you visualize this, and I actually kind of wish that I would put a picture. Maybe I should put a picture. I don't know. I can't decide. I'm going to show you a picture right now, and then we're gonna figure it out. I'm going to show you the picture just for a second, just to make sure that you have it very clear in your head. Okay, so this is our picture. Okay, new share. Here we go. Take a look at the picture. Okay, here's our main sequence. I'm sorry, here's the main sequence, this band right here. So this is what you're thinking about, right? So the lower end is cooler, the upper end is hotter. The lower end is lower in the luminosity scale. The upper end is higher on the luminosity scale. How about mass, right? We know that as you go higher, the mass is increasing. Lower, the mass is decreasing. How about the lifetime? The higher you go, the shorter the lifetime. The lower you go, the longer the lifetime. Remember, the smallest mass stars have lifetimes of 5.5 trillion years. And the ones that are 100 solar masses are 100,000 years. Our little sun, 10 billion years, okay? And going back to the question, okay? So does peak, oh, I forgot this, okay. I forgot to tell you this. One of the things you're supposed to know is, let's see, so surface temperature went up, that's true. The luminosity went up, that's true. Can't seem to highlight it. There we go. The mass went up, that's true. But what about the peak frequency? What about the fusion rate? Okay, so I feel like maybe just a quick, very tiny little quick review. Sorry, I know you guys are ready to be done. I'm done too. So just finish off though. If I look at something right here, Stefan Boltzmann, Oh, Stefan Boltzmann, yeah. Okay, if you guys remember, there's something called black body spectrum. And so let's look at that real quick. Okay, and then you'll get the two effects, okay? If you remember, this is the black body spectrum. The color of the star is a blending of all the colors we can see. The peak frequency changes. So the hotter the star, remember, you're supposed to remember this, hot stars, look what happened to the size of the peak. It got really, really big. But look at where the peak went. It went this direction. It actually went to what color? What color would the peak be? It would be ultraviolet. And that is a higher frequency than violet, right? So it shifts to a higher frequency. The color of the star appears blue as a result because there's more violet and blue light, less red, orange. If you go way down to the other extreme, right? Don't worry about the temperature not being right, but worry about the peak. Where's the peak? The peak is in the infrared. I can't even see. Okay, here we go. And there's some red and orange, but almost none of the violet and blue, so it looks red to our eye, okay? So these are cool stars. And so our final questions, what happens to the peak frequency? It goes up. That one's true as well. And why is it that more massive stars are hotter, right? Can anybody remember that? And the answer is because they are fusing at a greater rate. And that greater rate of fusion leads to a higher surface temperature, which also means higher luminosity. So the answer is all of these are true. Make sure you select every single one of them. Okay, everybody good? All righty, everybody got that? All right, well, thank you guys very much for being here. And I posted the exam and it opens at 12:01. Please don't take it then. Wait until you wake up in the morning. And then you can take it anytime during the day. You have 80 minutes unless you get extra time, in which case you get more time. And then just make sure you finish before midnight. Okay, so you are my students. You're going to do great. I know you're going to do wonderfully. And I wish you the best of luck. And then I will see you on Thursday at our regular lecture, 8 o'clock time. Okay, any questions? Thank you. Thank you for being here.
Thank you, Professor.
Okay, have a great night.
Bye.
Okay, sorry we went long.
That's okay. Thank you.
Okay,
Bye.
bye-bye. Bye. Bye.